Hello, welcome back to Sleep Science. Wherever you are right now, this is a good place to be. Tonight, we are going somewhere smaller than anything you have ever tried to picture. Settle in. There is something happening inside you right now that no one told you about. Not something wrong, nothing to worry about. Something so ordinary that science spent centuries not even knowing to look for it, and then spent the next century being genuinely unsettled by what it found. Every atom in your body, the ones in your hands resting on the blanket, the ones in the slow rise and fall of your chest, the ones behind your eyes that are growing heavy right now, every single one of them is doing something that should not, by any reasonable reading of the universe, be possible. They are not sitting still. They are not even really in one place, not in the way you might imagine an apple sitting on a table is in one place. The electrons orbiting the nucleus of every atom you are made of exist in something closer to a smear of probability than a fixed location, a kind of blur, a cloud of where they might be, hovering around the center of the atom, never quite committing to a specific point in space until something interacts with them, measures them, disturbs the quiet. This is not a poetic description. This is, as far as anyone has been able to determine, what is actually happening. Right now, in the atoms in your left hand, which is strange when you think about it. You feel your hand. You can press it against the mattress and feel resistance, feel pressure, feel the weight of your own body. Everything seems solid. Everything seems to be exactly where it is. And yet underneath all of that solidity, at the level where things are made of smaller things, and those smaller things are made of even smaller things, the rules are completely different. The rules are, in some ways, almost the opposite. This is what we are going to do tonight. We are going to go there, down to that level, down to the place where the familiar rules quietly stop working and something stranger, something genuinely odd, takes their place. Not because it is frightening, it is not frightening at all, but because it is true, and because the truth of it is somehow more restful than the version of reality we carry around in our heads during the day. The version where everything is solid and located and predictable. That version is useful. It helps you drive a car and catch a glass before it falls off the counter. But it is a kind of practical fiction, a useful shorthand. The deeper version, the one we are going to sit with tonight, is quieter, more uncertain, and somehow, because of that uncertainty, more at peace with itself. Let's begin somewhere very small, smaller than a grain of sand, smaller than a grain of anything, smaller than a cell, smaller than the nucleus of a cell, smaller than the molecules that make up the structures inside a cell. We are going all the way down to the level of the atom, and then further still to the things that make an atom what it is. And to do that properly, to really feel what we are talking about, rather than just nod at it from a safe distance, it helps to understand what an atom actually is. Which sounds like something you might have heard before in a classroom somewhere years ago. Diagrams on a chalkboard, little circles with rings around them, like a miniature solar system, an electron orbiting a nucleus the way the Earth orbits the Sun. That picture is helpful for some things. It is also, in an important way, quite wrong. Or at least, it leaves out the strangest part. The atom is not a tiny solar system. The electron does not trace a clean, predictable path around the nucleus the way a planet does around a star. The electron exists in something called an orbital, which is not a circle and not a path at all, but a region of probability, a shape, sometimes like a sphere, sometimes like a dumbbell, sometimes like something harder to describe, that tells you not where the electron is, but where it is most likely to be found if you look for it. Before you look, it is genuinely not in a single, specific location. This is the thing that took physicists decades to accept, because it sounds like nonsense. It sounds like saying the coin is not heads or tails until you look at it, which is fine as a metaphor for something you do not know yet. But what quantum mechanics is actually saying is something far more literal. The coin, before you look, is not just unknown to you. It is, in some real sense, not yet decided by the universe. The word scientists use for this is superposition, and we will come back to it, slowly and carefully, because it deserves time and space. But first, there is an experiment. A beautiful, simple, maddening experiment. One that has been called the most beautiful experiment in physics, and which was voted so by physicists themselves, which says something either about the experiment or about physicists, possibly both. It starts with light. Light, which you know as the warm glow behind your eyelids when the sun comes through a window in the morning, or the blue of a phone screen you should probably have put down an hour ago. Light, which seems like the most obvious, everyday thing. Light, which has been with you your entire life, every waking moment, and which it turns out is far stranger than it appears. The first version of this experiment, the one with light, was done by a man named Thomas Young, sometime around 1801. The exact year varies depending on which account you read, and I think the exact year matters less than what he found. What Young did was this. He took a source of light, a single beam, and he let it pass through two very narrow slits in a barrier. Behind the barrier, he had a screen. And what he expected, what any reasonable person in 1801 would have expected, was that the light passing through two slits would produce two bright bands on the screen behind. Two patches of light, one from each slit. That is not what happened. Instead, what appeared on the screen behind the barrier was a pattern. A series of alternating light and dark bands, many of them spread across the screen, a striped pattern. Now, if you have ever thrown two pebbles into a still pond, very close together, you will have seen something like what Young was looking for. The ripples from each pebble spread outward in circles, and when two sets of ripples meet, they interfere with each other. Where a crest from one ripple meets a crest from another, you get a bigger wave. Where a crest meets a trough, they cancel each other out. You get a complicated, interlocking pattern on the surface of the water. That interference pattern, that is what appeared on Thomas Young's screen, which told him, and which tells us, if we think about it carefully, that light was behaving like a wave, because only waves produce that kind of pattern. Only waves can interfere with each other in that way. Particles, if you fired them through two slits, would just make two piles, two bands. They would not cancel each other out, because a particle either goes through the left slit or the right slit, never both. So light, Young concluded, is a wave. And for about 100 years, that seemed to settle it, until it did not. Because in the early 20th century, a different kind of experiment suggested that light also behaves like a particle. The photoelectric effect, which won Albert Einstein a Nobel Prize in 1921, incidentally, not his work on relativity which everyone thinks about, but this, which is interesting in its own quiet way, showed that when light hits a metal surface and knocks electrons free from it, the way it does so can only be explained if light arrives in discrete packets, individual bundles of energy, not a smooth wave pouring in like water, but a stream of something more like bullets, each one carrying a fixed amount of energy depending on the frequency of the light. Einstein called these packets quanta. Later, they would be called photons. And the question that physics had now arrived at was uncomfortable and precise. Is light a wave, or is it a particle? And the answer, which took decades to fully accept, and which in some ways has never been fully accepted, even now, is that it is both, and neither, and something else entirely that we do not have a good word for in ordinary language. The word that got invented for it is wave-particle duality, which is a name for the fact, not really an explanation of it. You are still here, still breathing, the weight of the blanket across your legs, the small sounds of wherever you are, the way the air is just slightly cooler near the edges of the room. All of that is still happening, quiet and steady, while we go a little further into the strange. Let's go back to the experiment. Because Young's two-slit experiment, which started with light, was eventually repeated with something much harder to explain away: electrons. Electrons are, by any reasonable definition, particles. They have mass, they have charge, they are the things that flow through wires and make electricity work. When you think of a particle, an electron is a very reasonable thing to picture. Small, yes, absurdly small, but a thing that ought to have a location. In the early 20th century, physicists started firing electrons at barriers with two slits in them, in various increasingly careful experiments that built on each other over years. And what they found, what they kept finding, no matter how carefully they set things up, was the same striped interference pattern on the screen behind. The same pattern Young had found with light, the same pattern you only get with waves, which was already odd, because electrons are particles, not waves. But then someone thought to ask what would happen if you fired electrons one at a time. Not a beam, not a stream. One electron, then another, each one individually, with a gap between them, so that there is no chance of one electron interfering with another in flight. And the question behind this was, does a single electron, all by itself, still produce an interference pattern? Because if the interference is caused by one electron going through the left slit and another going through the right slit at the same time, and those two paths interfere with each other, then firing them one at a time should eliminate that. One electron, one slit, no interference. That is what you would expect. That is not what happened. When you fire electrons through a double slit one at a time, and you wait, and you watch where each individual electron lands on the screen, at first you see what looks like random dots. One here, one there, scattered. No pattern, just individual impacts. But as you fire more and more electrons, as the dots accumulate over minutes and hours, the picture that builds up is the interference pattern, the striped pattern, the wave pattern, even though each electron went through alone, even though there was nothing for a single electron to interfere with. Somehow each individual electron, each single particle, produces a result that over time adds up to what a wave would produce, as if each electron is, in some sense, interfering with itself, which means each electron must, in some sense, be going through both slits at once, not sneaking through one and then quickly through the other, not randomly choosing one or the other on a per-electron basis, because if it were randomly choosing, the pattern on the screen would just be two overlapping piles, which is not what you see. Each electron, before it hits the screen, must exist in some kind of spread-out state that passes through both slits simultaneously, a state that interferes with itself, a state that only resolves into a single definite location when it actually arrives somewhere and leaves a mark. This is not a theory about what the electron might be doing that we cannot see. This is the conclusion forced upon you by the actual results. The electron, in transit, is not a point in space. It is something more like a wave of possibility, a distribution of where it might end up, spread out, traveling through both slits, interfering with itself, and only collapsing into one specific location the moment it interacts with the screen. Let's stay here for a moment, because this is actually important. The electron is not hiding from you. It is not traveling through one slit, but you just happen not to know which one. The interference pattern is proof that it went through both. A particle secretly going through only one slit could not produce an interference pattern, no matter how long you waited. The math is very clear on this, and the math is confirmed by the results. So before it hits the screen, the electron genuinely has no single location. It is spread out, blurry, existing in multiple places at once, not as a metaphor, but as the closest description we have to what is actually true. Now, here is the part that makes physicists go very quiet. Someone had the idea to put a detector at one of the slits, a way to check which slit each electron went through. Not to block it, not to change where it went, just to observe, to look. And what happened when they added the detector? The interference pattern disappeared, just like that, clean, gone. With the detector running, the electrons started arriving at the screen in two piles. The pattern you would expect from particles that simply go through one slit or the other. The wave behavior was gone, replaced by particle behavior. Everything was normal and classical and boring. Turn the detector off. Interference pattern comes back. Turn it on. Gone again. The electrons seem to know they are being watched, which is the sentence that, understandably, makes everyone a little uneasy. Because what does it mean for an electron to know anything? What is actually happening when the act of measuring which slit the electron goes through causes it to stop behaving like a wave? This is, and I want to say this carefully, one of the genuinely unresolved questions in physics. Not in the sense that we do not have a good theory. Quantum mechanics as a mathematical framework predicts all of these results with extraordinary precision, but in the sense that what the theory is telling us about the underlying nature of reality is something that people continue to disagree about, quietly and seriously, more than 100 years after the experiments were first done. One part of the answer is that observation, in this context, does not mean a conscious mind watching. It means physical interaction. When you place a detector at a slit, that detector physically interacts with each electron as it passes through. That interaction, however gentle, however minimal, is enough. The universe is not responding to your consciousness. It is responding to physical entanglement with a measuring device. Probably, although the precise role of what counts as a measurement is itself a part of the ongoing debate, and there are serious, credentialed physicists who would add nuance to even that sentence. Not the mystical kind of nuance, not the consciousness creates reality version that gets popular on the internet, the careful, technical kind of nuance about exactly where the boundary between measured and unmeasured lies. We will come back to this. There is much more to unfold, but first, feel the weight of what was just said and let it settle. You do not need to resolve it. The physicists have not resolved it. The most brilliant minds to have ever sat with this particular question have come to different conclusions, and the different conclusions are all, in their own ways, internally consistent. That is allowed. The universe does not require your certainty in order to keep doing what it does. The blanket is still warm, your breath is still steady, and somewhere in the atoms of your fingertips, electrons are existing in precisely this kind of spread out, unresolved, waiting state. Not because you are made of something unusual, because this is what everything is made of. Let's talk about what the double slit result actually means, more carefully, because there is a layer underneath the experiment that tends to get passed over too quickly, and it is worth sitting in. When we say the electron goes through both slits at once, what we really mean is something a bit more precise and a bit more strange. We mean that the mathematical object we use to describe the electron, the thing called the wave function, the thing that encodes all the probabilities of where it might be and what it might be doing, that mathematical object does pass through both slits, and it does interfere with itself on the other side. and the interference pattern in the wave function is what determines the probability of where the electron ends up. The wave function is not the electron, or maybe it is. This is actually one of the deepest interpretive questions in all of quantum mechanics, and the question of what the wave function represents, whether it is a description of our knowledge about the electron, or whether it actually is the physical state of the electron in some fuller sense, is part of what distinguishes the different ways of interpreting what the theory is saying. The Copenhagen interpretation, which was the dominant view for most of the 20th century and is still the most commonly taught, essentially says, do not ask what the electron is doing before you measure it, because the question does not have an answer in classical terms. The wave function is a tool for calculating probabilities. When you measure, you get a result. That is what the theory gives you. The detailed story of what was happening before is not something the theory speaks to, which feels, to some people, a bit like saying, do not look too closely, and which frustrated certain people enormously, including Einstein, who was resistant to what he saw as the theory's refusal to give a complete picture of what was really going on. Einstein was not wrong to be frustrated, by the way. His frustration was precise and based on a real tension in the theory. He was wrong, or at least the experiments suggest he was wrong, about the direction that tension pointed. But he was not just being stubborn, he was asking a very reasonable question, and the answer turned out to be stranger than he was willing to accept. There are other interpretations. The many worlds interpretation, proposed by Hugh Everett in 1957, takes a very different approach. It says, the wave function is real, all of it. When an electron passes through the double slit and its wave function passes through both branches of that wave function are equally real. What happens at measurement is not that one outcome occurs and the others disappear, but that the entire system, electron, detector, room, you, branches into separate versions, each experiencing a different outcome. Every quantum event branches the universe, which sounds much more dramatic and alarming than the Copenhagen interpretation, but is arguably, if you accept it, more mathematically straightforward. There is no special moment of collapse. The wave function just keeps evolving, forever, all branches equally real, each unaware of the others. Neither of these interpretations, or the several others that exist alongside them, can currently be distinguished by experiment. They all make the same predictions. What they disagree about is the story behind the predictions. And so the question of what is really happening when an electron passes through two slits at once is not yet settled. It may not be settled in your lifetime. It may not ever be settled in the way we would like, and yet the electron keeps doing what it does, every time, with complete indifference to whether we have decided what to call it. There is something very restful about that, if you let yourself feel it. The universe proceeding without waiting for your interpretation. Now, the electron going through both slits at once is the most famous version of a more general phenomenon, which is the one that deserves its own long, careful look: superposition. The word itself is almost unhelpful, as I said before, because it sounds architectural, like the particle is layered, like two transparencies stacked on top of each other. It sort of conjures this image of two electrons in the same space, which is not quite it. A better way to think about it, though still imperfect, is to think of a coin spinning in the air. Not a coin that has been flipped and is on its way back down. A coin spinning freely, hovering, perfectly balanced, not falling, just spinning. Is it heads or tails? In ordinary life, the answer is, it is one of them, we just cannot see which one yet. The coin has a definite side facing up. It is simply moving too fast to read. Quantum superposition says something more radical. It says that before measurement, the question does not have an answer. Not, We don't know the answer, not the answer is hidden from us. But the system is in a state that includes both possibilities simultaneously, and the act of measurement, the act of letting the coin land, of looking, is what forces the outcome to become definite. And the disturbing thing, the genuinely strange thing, is that this is not just a story about coins and slits and electrons in labs. It applies to everything made of atoms, which is everything, including you. There is a very famous example of this that most people have heard of, even if they find it confusing, and it is worth spending some time here because it is usually described in a way that makes it sound much more alarming than it is actually meant to be. Schrödinger's cat. Erwin Schrödinger was one of the founders of quantum mechanics. He wrote down the equation that bears his name, the Schrödinger equation, that describes how quantum wave functions evolve over time. He was brilliant, central, essential. And he also proposed a thought experiment specifically designed to show how strange things get when you try to apply quantum rules to the scale of everyday objects. The thought experiment goes like this. You have a sealed box. Inside the box, you have a cat. Also inside the box, you have a radioactive atom, an atom that may or may not decay within the next hour. If the atom decays, it triggers a mechanism that releases a poison and the cat dies. If the atom does not decay, the cat is fine. Quantum mechanics says that before you open the box and check, the radioactive atom is in a superposition of having decayed and not having decayed. Both possibilities are simultaneously present in the wave function. But if the atom is in superposition and the atom's decay is linked to the cat's survival, then by the same logic, the cat must also be in a superposition, alive and dead, at the same time, until you open the box. Now, this is not meant to be a literal description of what is happening to a real cat in a real box. That is very important. Schrödinger proposed this thought experiment precisely to point out the absurdity, to show that applying quantum rules without modification to large, complex objects leads to conclusions that seem obviously wrong. A cat is not in a superposition of alive and dead. If you sealed a cat in a box for an hour and then opened it, the cat's status would not be undecided until you looked. The thought experiment is a challenge, not a description. It is Schrödinger saying, there must be something we are missing. There must be some principle that prevents quantum weirdness from scaling up to the world of cats and boxes and things we can see. Because clearly, it doesn't scale up. And yet the math does not obviously tell us why. The answer, the one that most physicists today find most satisfying, though it too has nuances, is called decoherence. And decoherence is something we will return to in much more depth later, because it is the bridge between the quantum world we are describing and the ordinary world you actually live in. But for now, the short version, a cat is made of something like 10,000 trillion atoms. Those atoms are constantly interacting with each other, and with the air inside the box, and with the walls, and with every photon of light, and every tiny vibration that passes through. Each of those interactions is a kind of measurement, a kind of entanglement with the environment. And when a quantum system becomes entangled with an enormous, complex environment, the quantum coherence, the delicate wave nature, the superposition, effectively dissolves, washed out, lost into the noise. The cat's quantum state, whatever it might technically be, is almost instantly and irreversibly tied up with so many other things that any quantum behavior becomes, for all practical purposes, invisible. The cat behaves classically. It is either alive or it is dead. You just do not know which until you open the box. And that, despite Schrödinger's worry, turns out to be the correct answer. the quantum strangeness happens. It just happens at a scale so small and resolves so fast that it is effectively invisible at the scale of cats and people and rooms. But at the scale of individual electrons, it is very visible, and it is very real. Your body, the slow warmth of it under the covers, the slight heaviness in your arms and your jaw, all of that is real and solid and classical in the way it has always been. But the atoms inside you are not. The atoms are doing what they always do, which is something closer to what we have been describing. Spread out, probabilistic, uncertain, and somehow, through an accumulation of billions of those uncertain little events, adding up to something that feels completely solid and located, and here, that is already a kind of miracle, even before we get to the stranger parts. And we are going to get to the stranger parts. Let's talk about something that Einstein spent the last 30 years of his life being bothered by. It started with a thought experiment he wrote with two colleagues, Boris Podolsky and Nathan Rosen, in 1935. The paper is usually referred to by their initials, EPR. And the thought experiment in the EPR paper was not designed to prove quantum mechanics wrong. It was designed to show that quantum mechanics, if taken at face value, must be incomplete, that it must be missing something, that the strangeness it described could not possibly be the full story. To understand what they were arguing, we need one more idea, a strange one, possibly the strangest one, entanglement. We will get to it properly, but first, one more step. When two particles interact in the right way, when they are created together in the same event, or when they collide and affect each other, something happens to their wave functions that is genuinely hard to describe in ordinary language. They become entangled. Their states become linked in such a way that from that moment forward, measuring one of them instantly tells you something definite about the other, regardless of how far apart they are. Not because information traveled between them, not because they signaled each other, but because they were never really separate to begin with, not in the way two ordinary objects would be separate. Einstein hated this. He called it spooky action at a distance, and he was, in his very precise way, asking, how does the second particle know, the instant the first one is measured, what result it should produce? Because if the particles are far apart, and we mean genuinely far apart, miles apart, potentially light years apart, there is no principle in quantum mechanics limiting the distance, and you measure the first particle, and instantly the second particle's outcome is determined. Something either traveled between them faster than light, or the outcomes were determined all along, or something else is happening. Einstein believed it was the third option, that there must be hidden variables, pieces of information already encoded in both particles at the moment they separated, deciding in advance what each one would produce when measured, like a pair of gloves sent to different cities in separate boxes. You open one box, you find the left glove, you immediately know the other box contains the right glove, not because information traveled, because they were always that way. It is a sensible explanation. It turns out to be wrong. A physicist named John Bell, in 1964, found a way to test it. Bell's theorem showed that if hidden variables of the ordinary kind were responsible for the correlations between entangled particles, the correlations would have to obey certain limits, certain statistical boundaries. There are specific experimental setups where hidden variable theories predict one range of results, and quantum mechanics predicts another, and the two ranges do not overlap. An experiment was done, and then more experiments, better ones, with fewer loopholes, with increasing precision, and every time the results came out on the quantum mechanics side, not the hidden variable side, not the Einstein side. The correlations between entangled particles are stronger than any hidden variable theory allows for. The gloves in separate boxes explanation does not work. The particles were not carrying the answer with them when they separated. The outcome really is decided at the moment of measurement, and the two particles really are correlated in a way that nothing in our ordinary intuitions of space and causality fully accounts for, which leaves us with a genuinely uncomfortable conclusion. Entangled particles are not separate things, not in the usual sense. Even when they are very, very far apart, something about them remains connected, a correlation built into the structure of reality in a way that has no classical analog and no satisfying ordinary language explanation. And yet it cannot be used to send information. This is crucial, and it is worth saying clearly. Quantum entanglement does not allow faster-than-light communication, ever. When you measure your particle, you learn something about the other particle. But you cannot control what outcome you get. The result of your measurement is random, so from the point of view of someone watching the other particle, they just see a random result too. There is no way to use that randomness to encode a message. The correlation only becomes visible when you bring the two sets of results together afterwards and compare them. That comparison has to happen through ordinary channels, which travel no faster than light, so the spookiness is real. But it cannot be weaponized into a telephone. The universe seems to have arranged things so that entanglement is genuinely strange, genuinely non-local in some deep sense, and yet completely useless for sending signals faster than light, which is either a remarkable coincidence or a profound structural feature of how reality is put together. The night is deep and still. If you have a window nearby, the dark outside is the same dark that has always been there, indifferent and patient, full of something like the strangeness we have been describing, the universe continuing its quantum business at every scale, from the smallest particles to the largest structures, all of it proceeding without anyone's permission. Your breathing is slower now than it was when we started. That is a good sign. We are just getting deeper into this. Let the thoughts settle where they land. None of this needs to be fully grasped tonight. The physicists themselves have not fully grasped it. You are in good company. Let's stay with entanglement for a moment longer, because there is something in it worth sitting with. When two particles become entangled, the standard way to describe what happens is to say that they no longer have independent quantum states. Before entanglement, each particle has its own wave function. After entanglement, there is a single wave function that describes both of them together, and this combined wave function cannot be factored apart into a wave function for the first particle times a wave function for the second. They are mathematically inseparable, which is a strange kind of thing to be. Two particles, possibly on opposite sides of a room, possibly on opposite sides of a planet, possibly, in principle, on opposite sides of a galaxy, and yet described by a single mathematical object that cannot be divided into two independent parts. The question of what this means for the underlying nature of space, whether entangled particles are somehow close to each other in some deeper sense even when they are spatially far apart, whether the structure of space-time itself is in some way built from entanglement, is something that physicists and theorists are actively exploring right now. These are not crazy speculations. They are serious, ongoing programs of research. The relationship between quantum entanglement and the geometry of space-time is something that comes up in attempts to reconcile quantum mechanics with general relativity, which is the other great pillar of modern physics. The two theories work beautifully in their own domains. Quantum mechanics at the small scale, general relativity at the large scale, but they do not, as yet, fit together into a single framework. And one of the places people look for the seam is somewhere in this question of what entanglement means for the fabric of space. We will not go all the way down that road tonight. It is very dark down there, and the road does not yet have an end. But the fact that it exists, that there is a place at the frontier of physics where entanglement and gravity are quietly suspected of being related, is worth knowing. It means we are not done being surprised. Let's come back to something simpler, or at least something more intimate. Superposition again, because we skated past it a little quickly in favor of the experiments, and superposition deserves its own full conversation. What does it mean for something to be in two states at once? The honest answer is that the phrase "two states at once" is already a compromise. The English language was built for a world of solid objects and definite locations, and the quantum world does not cooperate with that vocabulary. A better framing, perhaps, is to say that before measurement, a quantum system does not have a definite value for certain properties. Not has a definite value that we do not know, has no definite value. The electron's spin, its orientation, whether it is aligned with a magnetic field or against it, which we sometimes call up or down, before you measure it, is not up, it is not down. It is not secretly one or the other while waiting for you to check. It is in a quantum state that includes both possibilities, weighted by probabilities, and the measuring process is what actualizes one of them. Spin is a good property to think about here because it is a very clean example. An electron has spin, which is a kind of intrinsic angular momentum. When you measure the spin along a given axis, you get one of exactly two results, up or down. Never a fraction, never an intermediate value, always one or the other, even if before the measurement the electron was in a superposition of both. The probabilities can be different. You can have an electron that is, say, 70% likely to be spin up when measured and 30% likely to be spin down, but it still gives you one or the other, never a weighted average. And before measurement, it genuinely had neither. That is superposition. The question of what happens to the other possibility, the one that did not get actualized, is precisely where the Copenhagen interpretation and the many worlds interpretation diverge. Copenhagen says, the other branch of the wave function collapses, vanishes, was never physically real in the first place. Many worlds says, the other branch is just as real, and the universe has split into two versions, one for each outcome, and you and your measuring device are now part of the version that got spin up, while another version of you is equally real in the branch that got spin down. Both answers are internally consistent. Neither is provably correct with current tools. And so the physics community lives with this ambiguity, for now, and mostly chooses not to look at it too directly when doing actual calculations, because the calculations work either way. The calculations work. That is a sentence worth pausing on. The math of quantum mechanics, despite the deep philosophical confusions about what it means, produces predictions that are correct to an extraordinary number of decimal places. The theory, as a practical tool, is the most precise and accurate theory in the history of science. Its predictions have been tested and confirmed more thoroughly than any other physical theory we have ever built. We just do not fully agree on what it is telling us about reality, which is, depending on your temperament, either deeply frustrating or deeply interesting, probably both. Outside, if there is a window, the night is the same night. Something about this being the exact same darkness that Bohr and Heisenberg argued in, that Einstein stayed up late worrying in, that young graduate students in dim offices all over the world tonight are still puzzling over. The same darkness, the same atoms. We should talk about Heisenberg now, because there is a principle named after him that is one of the most widely misunderstood ideas in all of physics, and misunderstanding it deprives you of something genuinely lovely, the Heisenberg uncertainty principle. Most people have heard of it. Many people think they know what it means, and the version most people think they know is something like, you cannot measure something very precisely because the act of measuring disturbs it. That is not wrong exactly, but it is too small, too tame. The real principle is something more fundamental. It says that certain pairs of properties, position and momentum, most famously, but also energy and time, are linked in such a way that they cannot both be known with perfect precision simultaneously. Not because our instruments are imperfect, not because the measuring process disturbs the system, but because a more precise value for one property corresponds, at a fundamental level, to a less defined value for the other. This is a feature of what the properties are, not of how we measure them. Here is one way to feel this without mathematics. A wave. Think of a wave on the ocean. A single wave, long and smooth, rolling in from far away. If you wanted to locate that wave, to point to exactly where it is, you would have some difficulty. A wave is not a point. It is extended. It is spread across a region of space. You might say, around here, and gesture at a stretch of water. But that long, smooth wave has a very precise frequency, a very well-defined wavelength. The pattern is regular and measurable. Now think of the opposite. A very sharp, sudden disturbance in the water, almost a spike, like someone dropped a pin, a very localized thing with a well-defined position. Here, exactly here. But mathematically, a sharp spike is not made of a single frequency wave. It is made of many frequencies superimposed, many waves of different wavelengths all added together in just the right combination to produce that sudden spike. If you want to be very localized, you need a broad mix of frequencies. This is not a limitation of the ocean, it is a mathematical fact about waves. And particles, at the quantum scale, are described by waves, by wave functions, and so the same mathematical relationship applies. A particle with a very well-defined position, a very localized wave function, necessarily has a very spread-out momentum. Many momenta mixed together, and a particle with a very well-defined momentum, a very regular smooth wave function, necessarily has a very spread-out position. It is everywhere. The uncertainty is not imposed from the outside, it is written into the nature of waves, which everything at that scale fundamentally is. Heisenberg's principle, in this light, is not about our ignorance or our limitations, it is about the genuine indeterminacy of nature. Position and momentum, for a quantum particle, are not two separate things that both exist independently and just happen to be hard to know at the same time. They are properties whose very existence is entangled, whose precision is a zero-sum game built into the fabric of what it means to be a wave, more precisely positioned, less precisely momentumed, not because one affects the other, because they are, in a very deep sense, two sides of the same mathematical coin. Einstein struggled with this. His belief in a complete, deterministic reality underlying quantum mechanics, a reality where everything has definite values whether we look or not, was never something he fully let go of. The uncertainty principle for him was a symptom of incompleteness, evidence that the theory was not yet the final word, and yet every experiment done since his death has confirmed the uncertainty principle as a genuine feature of nature, not a gap in our knowledge. Which means the universe, at its smallest scale, is genuinely, irreducibly uncertain. Not a machine we cannot quite see inside, something more like a process that has not finished deciding yet. Every moment, without end. And you, right now, in the quiet of wherever you are, made of exactly that kind of process, down to the most fundamental level. The atoms in your hair, the atoms in your teeth, the iron in your blood, the calcium in your bones, all of it uncertainly located, probabilistically spinning, quantum mechanically spread out into clouds of possibility that only appear solid and definite at the scale you can touch and see. The solidity is real, and the uncertainty is also real. They coexist without contradiction. Let's slow down even more. We have talked about the double slit, about superposition, about the uncertainty principle, about the beginnings of entanglement. We have moved through these ideas at a reasonable pace for a conversation, but the ideas themselves deserve more room than a summary can give them, and one of the things about tonight is that there is nowhere to rush to. So let's return to something: the double slit experiment, and the question of what happens when a detector is placed at the slits. We said the interference pattern disappears, the wave behavior collapses into particle behavior, the electron goes through one slit or the other, definitively, when something is there to check. But there is a variation of this experiment that is even stranger, in a way that tends to stop people cold when they hear it. It is called the quantum eraser. The quantum eraser experiment takes the basic double slit setup and adds a twist. It makes it possible to detect which slit the particle went through, and then, after the particle has already hit the screen, erases the which path information, and asks, what happens to the interference pattern? The answer, which has been confirmed in several careful experiments, is that erasing the which path information restores the interference pattern, not retroactively, not in the sense that it changes the past, but in the sense that when you sort the results, when you separate the particles whose which path information was erased from those whose was not, the erased group shows an interference pattern and the non-erased group does not. The pattern depends on what you do with the information, not even on whether you observe the particle directly, on what you do with the knowledge, even after the fact. This is the part where it becomes genuinely difficult to hold the intuition together. The particle has already arrived at the screen by the time you decide what to do with the which path information. And yet whether you erase that information seems to matter for whether its arrival was part of a wave pattern or not. What is actually happening here is a careful matter of quantum mechanics and correlations, and the math handles it cleanly. What it means, philosophically, for the relationship between information, knowledge, and physical reality is another question that is still being turned over. What the quantum eraser does not mean is that the future causes the past. The pattern only appears when you sort the data afterwards. A single particle arriving at the screen does not carry any sign of whether it was part of a wave or not. It is only in the correlation between what happened at the detector and what happened at the screen, correlated after the fact, that the pattern emerges or disappears. But that said, there is something in it, something about the relationship between information and physical outcomes that is not fully resolved in ordinary language, and which is, quietly, still being thought about. One more thing about superposition before we go deeper. Schrödinger's cat introduced the idea that quantum rules, applied to large systems, seem to predict things that are obviously wrong, and decoherence is the mechanism by which quantum behavior dissolves at large scales. But there is something in the story of the cat that gets passed over, which is worth bringing back. The reason Schrödinger was frustrated, the reason the thought experiment bothered him, was not that he thought cats might actually be alive and dead at the same time. It was that quantum mechanics, as formulated at the time, did not tell you when the superposition stopped. There was no clear rule about what counted as a measurement, no clear line between the quantum world where superposition holds and the classical world where things are definitely one thing or the other. This is still not fully resolved. Decoherence explains, beautifully and in great mathematical detail, why quantum behavior effectively disappears at large scales. How the entanglement between a system and its environment causes the interference between different branches of the wave function to become, for all practical purposes, impossible to observe. But decoherence does not, by itself, tell you why you get one outcome. It tells you why the other outcomes become invisible. It tells you why the cat seems to be alive or dead, rather than in a superposition. But the question of why this particular cat, in this particular box, turned out to be alive rather than dead, rather than the other way around, that question, the question of why any specific outcome occurs at all, remains, very genuinely, open. This is called the measurement problem, and it is one of the oldest unsolved problems in the foundations of quantum mechanics, which is a field that is, despite being more than 100 years old, still producing genuine surprises. There is something almost comforting about that. 100 years, the best minds, the most precise experiments in human history, and still, some of the deepest questions about what is actually happening remain. Not because we lack evidence, but because the evidence keeps pointing somewhere the language cannot quite follow. The universe has been doing this for a very long time before anyone tried to understand it, and it will keep doing it regardless of whether understanding ever arrives. That, somehow, is a peaceful thought, or at least it becomes one if you let it sit long enough. There is a version of the uncertainty principle that most people never hear about, and it is the one that, in some ways, hits closest to home. Not the position momentum version, though that one is important, and we have spent some time with it already. This other version involves energy and time. The energy-time uncertainty relation says something very odd. It says that over very short timescales, the energy of a system is not precisely defined. There is a kind of inherent blur in how much energy a region of space contains at any given moment. And the shorter the time you are talking about, the larger that blur can be. What this means in practice is something almost hallucinatory. Empty space is not empty. The vacuum, space containing nothing, no particles, no matter, no radiation, is not a flat, featureless nothingness at the quantum level. It is more like a surface of a pond during a very light rain, constantly rippling with tiny, transient fluctuations of energy. Pairs of particles can briefly pop into existence from nothing, exist for an almost unimaginably short time, and then annihilate back into nothing. They are called virtual particles, and they are not hypothetical or theoretical in the way that might sound. They have measurable effects. One of those effects has been confirmed in a laboratory. It is called the Casimir effect. If you take two very flat metal plates and bring them extremely close together in a vacuum, not touching, just very close, separated by a distance measured in nanometers, billionths of a meter, they will be attracted to each other by a tiny force, even though there is nothing between them to pull them together. The explanation is that the virtual particle fluctuations in the vacuum are slightly different inside the gap between the plates than outside it. Inside the very small space between them, only virtual particles with certain wavelengths fit. Outside, all wavelengths are available. This difference in the pressure of quantum vacuum fluctuations on either side of each plate produces a net force pushing the plates toward each other. This has been measured. It is real. Empty space pushes, which means the vacuum itself, the stage on which everything in physics happens, is not a passive backdrop. It is an active participant, humming with quantum fluctuations, never truly still, never truly empty. This should fundamentally change the way you picture nothing. We think of nothing as an absence, a blank, but quantum nothing is full of something. Something temporary, fleeting, constantly emerging and vanishing, a kind of froth of possibility at the most fundamental level. And the universe we live in, with all its matter and energy and structure, may, in a very real sense, have emerged from exactly this kind of fluctuation. In the early moments of the universe, when everything was compressed into an almost unimaginably small and dense state, quantum fluctuations in the distribution of energy would have been present. Those fluctuations, stretched and amplified by the expansion of the early universe, are thought to be the seeds of all the structure we see today. The variations in density that eventually, over billions of years, became galaxies and clusters of galaxies and the vast web of cosmic structure. The largest things in the universe may be the stretched-out echoes of quantum fluctuations. The great emptiness between galaxies tracing a pattern that began with something smaller than anything we can touch. That thought deserves a moment. The distribution of matter across the observable universe, all of it, everything that is and has ever been, may be, in its deepest origin, a quantum accident, a ripple in the vacuum, made very, very large. Your body right now, lying wherever you are lying, is itself the product of a chain that traces back through the history of the universe to events at the quantum scale. The atoms you are made of were forged in stars. The stars formed because matter clustered along the paths of ancient density fluctuations. Those fluctuations originated in the quantum noise of the early universe. You are, in some sense, a quantum fluctuation that became complicated enough to wonder about its own origin, which is not a mystical statement. It is almost a literal one. Let's come back down to the scale of ordinary experiments, because there is still much here to unfold. We talked about the double slit. We talked about superposition and the uncertainty principle. We touched the surface of entanglement. But there is another quantum phenomenon that most people have heard less about, and which in some ways is even more immediately connected to everyday life. Quantum tunneling. The name sounds technical, and the concept sounds like something from a science fiction film, but the reality of it is something that happens inside the sun, every second, on a scale that is keeping you alive. Here is the problem tunneling solves. In classical physics, if a particle is moving and it encounters a barrier, an energy barrier, a region where it would need more energy than it has to get through, it bounces back. It cannot cross. It simply does not have enough energy. This is how a ball rolled toward a hill. It is not fast enough to crest, will slow down, stop, and roll back. Quantum mechanics says something different. It says that a particle described by a wave function, when it encounters an energy barrier, does not simply stop at the barrier. Its wave function penetrates the barrier. It extends through it, decaying in amplitude, becoming smaller and smaller, but never quite reaching zero inside the barrier. And on the other side of the barrier, the wave function has a small but non-zero amplitude, which means there is a small but non-zero probability of finding the particle on the other side, without it ever having had enough energy to classically cross. It tunneled through, not around, through. This is not an approximation or an idealization. It is something that happens, and it happens constantly, and without it the sun would not shine. The sun fuses hydrogen into helium in its core, releasing the energy that radiates outward and eventually reaches the Earth and keeps everything alive. But this fusion requires two protons, two positively charged particles, to get close enough to each other to be within range of the strong nuclear force, the force that holds atomic nuclei together. Two positively charged particles repel each other electromagnetically. The closer they get, the stronger the repulsion. To get close enough for the strong nuclear force to take over, they need to overcome an enormous electromagnetic barrier. Calculations show that the temperature in the core of the Sun, about 15 million degrees, is not actually hot enough for protons to have the energy required to classically overcome that barrier. And yet fusion happens, the Sun shines. Because the protons tunnel through the electromagnetic barrier, the probability of any given pair of protons tunneling through is very small. But there are so many protons in the Sun's core, and they are colliding so frequently, that tunneling events happen constantly. A vast, distributed, quantum probabilistic process, generating the energy that has lit the Earth for 4.5 billion years. The Sun is powered by quantum probability. This is not a metaphor. Every photon of sunlight that has ever landed on your skin arrived here because quantum tunneling made fusion possible. The warmth you have felt on your face on a summer morning, on a concrete step, through a car window, all of it, ultimately, from a quantum process in the core of a star. Feel that for a moment. The quantum world is not separate from ordinary life. It is embedded in every part of it. And tunneling is not just happening in stars. It happens in the chemistry of DNA. When certain chemical reactions occur in living cells, tunneling assists the movement of protons and electrons across energy barriers they might not otherwise be able to cross efficiently. The role of quantum mechanics in biology is a young and genuinely uncertain field, and I want to be careful not to overstate what is known. But there are serious, ongoing research programs looking at whether quantum effects play a functional role in photosynthesis, in enzyme catalysis, and possibly in other biological processes. What seems clear is that tunneling happens in living matter. To what extent it is functional, rather than incidental, is something still being sorted out. But the fact that it happens at all, inside cells, inside the molecules that make you alive, is already remarkable. There is also a more mundane, but more immediately verifiable place where tunneling matters enormously: modern electronics. The transistor, the fundamental switching element of every electronic device, every computer, every phone, every piece of digital technology ever made, works, in a certain sense, because of quantum mechanics. At the scale of modern transistors, which are now only a few nanometers across, quantum effects are not exotic anomalies. They are engineering constraints. The behavior of electrons at that scale cannot be described without quantum mechanics. And one of the things engineers working at that scale have to account for is precisely tunneling. Electrons can tunnel through the thin insulating layers inside transistors, causing current to leak where it should not. At the scale of the earliest transistors, this was not a significant problem. But as transistors have gotten smaller and smaller, as the industry has pushed to fit billions of them onto a chip the size of a fingernail, tunneling has become one of the fundamental limits on how small they can go. The quantum world is reaching up through the machinery of technology and saying, this far and not further, which is in itself a kind of strange comfort. The universe has rules at the smallest scale, and those rules are not infinitely elastic. There are limits that are not engineering challenges, but physical facts. And those physical facts are going to shape the future of computing in ways that are still being worked out. Which brings us, gently, to quantum computing. Though let's be careful here, because quantum computing is a topic that attracts a certain amount of breathless overstatement, and tonight is not the night for breathlessness. Ordinary computers, classical computers, the kind in every phone and laptop and data center, work by processing information encoded as bits, zeros and ones. Each bit is in one state or the other at any given time. A sequence of bits encodes information and instructions, and the processor manipulates those bits very quickly to produce results. A quantum computer, by contrast, uses quantum bits, qubits. A qubit can be in a superposition of 0 and 1 simultaneously. It is not hiding its value. It genuinely, before measurement, holds both possibilities at once. And multiple qubits in superposition, entangled with each other, can represent and process an enormous number of states simultaneously. This makes certain kinds of problems, certain specific classes of mathematical problems, potentially much more tractable on a quantum computer than on a classical one. The emphasis is on certain specific classes. A quantum computer is not faster at everything. It is not a universally better kind of computer. For most everyday tasks, browsing the web, writing a document, watching a video, a quantum computer would offer no advantage. The advantage shows up for specific things: searching large unsorted databases efficiently, simulating quantum systems, which is enormously useful for drug discovery and materials science, factoring large numbers, which is relevant to cryptography. The current state of quantum computers is something like the state of classical computers in the very early days, when they filled rooms and could only do specific, narrow tasks. Quantum computers today exist and function, but they are still prone to errors, still require extreme isolation from the environment to maintain quantum coherence, still limited in the number of qubits they can reliably control. Progress is real. The current capabilities are limited. Both of those things are true at the same time, which seems appropriate for a technology built on superposition. Let's talk about what quantum mechanics says about identity. This is not usually a topic in physics lectures, but there is something in it that is worth sitting with in a quiet moment. Ordinary objects have identity. This cup is this cup. If I swap it with another cup of the same type, something has changed, even if no one can tell by looking. The cups are different objects, even if they are identical in every measurable way. Quantum particles are not like this. Two electrons are not just very similar, they are, in a precise quantum mechanical sense, literally identical, indistinguishable, not just hard to tell apart. Indistinguishable in a way that matters physically, in a way that changes how they interact, in a way that has measurable consequences. When two electrons approach each other, quantum mechanics treats their wave function as a single mathematical object that is symmetric or antisymmetric under the exchange of the two particles. This means there is no fact of the matter about which electron is which. The physics does not distinguish them. They do not have individual identities in the way that two people or two cups do. This is called quantum indistinguishability, and it has profound consequences. The reason electrons in an atom arrange themselves the way they do, the reason they fill up energy levels in a specific pattern, the reason atoms of different elements have different chemical properties, the reason the periodic table is structured the way it is, all of this is a consequence of the Pauli exclusion principle, which itself arises from the indistinguishability of electrons. The Pauli exclusion principle says that no two electrons in the same quantum system can occupy the same quantum state, same energy level, same spin, same orbital. Two electrons, fine. Three electrons, they can still be distinct in different states, but never two in exactly the same state. This is why electrons pile up in shells around the nucleus. The first shell can only hold two electrons, because the lowest energy level has only two possible spin states. The second shell can hold 8, and so on. The arrangement of electrons in shells determines almost everything about how atoms interact chemically. Chemistry is a consequence of quantum indistinguishability. The fact that water is wet, that salt dissolves in it, that your blood carries oxygen and releases it to your cells, that DNA can be copied and read, all of this chemistry, All of these specific interactions depend on the rules that electrons follow because they are indistinguishable quantum particles governed by the Pauli exclusion principle. Without quantum indistinguishability, there would be no periodic table. Without the periodic table, there would be no chemistry. Without chemistry, there would be no biology. Without biology, there would be no you, lying here at the end of a day that has slowly been folding itself into night. The quantum indistinguishability of electrons is one of the reasons you exist, not in a poetic way, in a structural, physical, causal way. The abstract seems very close in moments like that. The deep rules of matter touching the surface of a life so directly that the two feel like the same thing, which, in some sense, they are. Everything is the same thing at a deep enough level. Different patterns of the same underlying quantum fields, following the same rules, producing the remarkable variety of what is. Quantum field theory, which is the deepest framework we currently have for understanding particles and forces, treats all particles as excitations of fields. The electron is not a little ball floating in space. It is a vibration in the electron field, which fills all of space uniformly. When an electron exists somewhere, it is because the electron field at that location has been excited. The photon is an excitation of the electromagnetic field. There is a field for every type of particle, stretching through all of space, at every point, right now. The room you are in is full of fields, some of them vibrating slightly, because there is light in the room, or was earlier, photons bouncing around. The electron field at every point in the room, including inside your body, at a constant background level, the various quark fields, and the gluon field that mediates the strong force between quarks. Neutrino fields, with their excitations barely interacting with anything. The universe is not mostly empty space with a few particles in it. The universe is mostly fields, and the particles we talk about, electrons, photons, protons, are local disturbances in those fields. Ripples in fields that fill all of space, including the space you are occupying, including the space between your atoms, which is most of the space of you. You are, at this level of description, mostly fields, with very small disturbances in them. Your specific arrangement of disturbances, your particular pattern in the fields, producing the sensation of weight and warmth and breath and thought. One specific configuration, out of all the possible configurations, briefly and improbably sustained, and in that brief sustaining, somehow aware of the fields it is made of, which is the thing that may be the strangest of all. Not the superposition, not the entanglement, not the tunneling or the uncertainty or the vacuum fluctuations. The strangest thing may be that the fields are aware of themselves, that the universe, through a particular arrangement of its own quantum excitations, has produced something that can sit quietly in the dark and wonder about quantum mechanics. That can follow an idea down through layer after layer of strangeness and arrive somewhere that feels, if not like understanding, then at least like familiarity, like recognizing a face you have not seen in a long time. Let's hold that gently and keep going. We talked about the double slit and what happens when a detector is placed at the slits. We talked about the quantum eraser and how erasing which path information seems to restore the interference pattern even after the particle has already arrived. These are experiments done in labs with photons and electrons and very careful equipment. But in recent years, experimenters have been pushing the boundaries of which systems can show quantum behavior, and the results are interesting. Interference has been demonstrated not just with electrons and photons, but with atoms, and then with molecules. In experiments done in Vienna, starting in the late 1990s and continuing since, a team led by Anton Zeilinger and later by Markus Arndt showed interference patterns produced by molecules. First, a carbon molecule called Buckminster fullerene, 60 carbon atoms arranged in a sphere, sometimes called a buckyball. Then larger molecules, then larger still. As of the most recent experiments I am aware of, interference has been demonstrated with molecules containing hundreds of atoms, moving through a double slit as a wave, producing an interference pattern on a detector screen. Not a single particle, a molecule, something you could, in principle, see with a very powerful microscope, showing wave-like behavior, at room temperature, or close to it, with careful enough isolation from the environment. This is not magic, it is decoherence management. The experimenters work very hard to isolate the molecules from interactions that would cause decoherence, from stray gas molecules in the vacuum chamber, from stray photons, from vibration. They are essentially keeping the quantum coherence alive long enough for the molecule to travel from the source to the screen. But the fact that they can do it, and that it works, and that the interference pattern appears, tells us something important. There is no sharp line. There is no clearly defined size or complexity at which quantum mechanics stops applying. The transition from quantum to classical is not a wall. It is a gradient, a continuum. The larger and more complex a system is, the faster and more completely decoherence occurs. But the quantum rules are always there, always in principle producing quantum effects, just washing those effects away faster and faster as the system grows. This means the distinction between the quantum world and the classical world is not a distinction between two different kinds of physics. It is a distinction between two different regimes of the same physics. Two ends of a spectrum, not a border crossing, which suggests that the weirdness we attribute to the quantum world is not a special property of small things. It is a property of everything, just most visible at the small end, like the fine texture of a piece of fabric. Up close, you see the individual threads, the way they are woven, the gaps between them. From a distance, you see only smooth cloth. The texture is still there. The gaps between the threads are still there. The fabric has not changed, only your distance from it. The quantum texture of reality is like that. You are always inside it, always made of it, just usually too large to feel the individual threads. Now, let's go back to entanglement one more time, because there is something we passed over that deserves its own moment. When two particles are entangled, and you measure one, you instantly know something about the other. We said this does not allow faster-than-light communication, and that is true, but there is a subtler thing hiding underneath, which is worth slowing down to look at. When you measure one of the entangled particles, the result you get is random, not just unpredictable. Random in the deepest sense quantum mechanics allows. There is, as far as the theory says, no prior fact about what result you will get. The probability is determined by the wave function, but within that probability, the specific outcome, spin up or spin down say, has no prior cause. It simply occurs, and the moment it occurs, the other particle's state is determined, across whatever distance separates them, not because a signal traveled, but because they were described by a single wave function, and that wave function does not have a location in the ordinary sense. The question of whether the correlation between the two measurement results was somehow established in advance, secretly carried by the particles from the moment of their creation, was exactly what Bell's theorem was designed to test. And the experiments showed, no, it was not established in advance. The correlation was not pre-written. It was created, both sides of it simultaneously, at the moment of measurement. Both outcomes instantaneous. No signal, no hidden cause, just the universe deciding, at the moment of measurement, what both particles will have been. The phrase, Will have been is grammatically strange, and I use it on purpose. Because there is something in entanglement that sits oddly with ordinary notions of time and causality. The two measurement events, even if they are far apart in space, are connected in a way that does not respect the ordinary picture of causes flowing from earlier moments to later ones. The correlation is not caused by the earlier entanglement, the way a ball rolling off a table is caused by the nudge that set it rolling. The correlation seems to exist outside that kind of causal chain. This does not mean causality is broken. It means entanglement reveals that our ordinary picture of causes and effects and the orderly passage of time from past to future is, like the solidity of the table, a very good approximation that breaks down when you look closely enough, deeply enough, far enough in. The ordinary picture, the one where everything has a location, everything has a definite state, every event has a prior cause, time moves cleanly from before to after, is useful. It is good enough for almost everything you will ever need to do. But it is not the final word. The final word, if there is one, includes superposition and uncertainty and entanglement and non-locality, and is written in the language of wave functions and probability amplitudes, and it describes a reality that is stranger and more connected than the ordinary picture suggests. Which is fine. The ordinary picture does not need to be the final word in order to be useful. A map does not need to show every rock and route to be a good map. It just needs to serve the purpose you are using it for. And for the purpose of living a life, the ordinary map is excellent. For the purpose of understanding what matter and energy and space actually are, the map needs more detail. And when you add the detail, the map becomes remarkable. Let's go a little further into the physics of atoms, because there is something in there that connects what we have said about quantum mechanics to the actual structure of matter in a way that I think is beautiful. We know that atoms have a nucleus and electrons. We know that electrons do not orbit the nucleus the way a planet orbits a star, but instead exist in probability clouds called orbitals. We know that no two electrons can be in the same quantum state. But why are there specific energy levels? Why do electrons only occupy certain discrete energies in an atom rather than any energy at all? The answer comes back to waves. An electron in an atom is a wave, and a wave in a confined space, a wave that must fit inside a boundary, can only have certain wavelengths. Think of a guitar string, fixed at both ends. When you pluck it, it vibrates at its fundamental frequency and at harmonics of that frequency, wavelengths that divide evenly into twice the string's length. Any other wavelength would not fit. It would not form a standing wave between the fixed ends. An electron around an atom is similar. The electron's wave function must be a standing wave around the nucleus. It must fit around the nucleus in a way that closes on itself. Only certain wavelengths can do this. And because the wavelength of the electron determines its energy, only certain energies are available. Discrete energy levels, quantized, the origin of all of chemistry. When an electron drops from a higher energy level to a lower one in an atom, it releases the energy difference as a photon, a particle of light, and the energy of that photon determines its wavelength, its color. Different elements have different sets of energy levels, determined by their nuclear charge and the arrangement of their electrons, and so each element has a unique set of energy differences available, and therefore emits and absorbs light at a unique set of wavelengths, a unique spectral fingerprint. And because every atom of a given element everywhere in the universe has the same structure, the same energy levels, the same spectral fingerprint, astronomers can look at the light coming from a star millions of light years away and determine, from the specific wavelengths of light that are absent or present, exactly which elements that star is made of. From here, reading the quantum fingerprint of atoms in a star we will never visit. Hydrogen's fingerprint in the light of a star, 100 million light-years distant, is the same as hydrogen's fingerprint in the light of a lamp in a laboratory. The quantum energy levels of hydrogen have not changed. Distance does not matter. Time has not changed them. Hydrogen, 1 billion years ago, emitted the same wavelengths as hydrogen does today. The quantum rules are not local, and they are not temporary. They are the same everywhere, at every time we have ever been able to check, which is its own kind of astonishing thing. The universe has been playing by the same rules since at least the first few 100,000 years after the Big Bang, when atoms first formed and their electron transitions first became possible. The same rules, everywhere, always. You could observe a galaxy at the edge of the observable universe, light that has been traveling for 13 billion years, and the quantum fingerprints in its spectrum would match the ones in a lamp on a laboratory bench. The consistency of the universe. Not just that it has rules, that it has the same rules in every direction, at every distance, across all of time we have access to, that is not guaranteed. There is no reason, from first principles, that the rules had to be the same everywhere. They just are. As far as we can tell, which is far enough, for now, the steady hum of a universe playing by consistent rules, without being asked to, without a reason we can fully name. There are moments when physics is very humbling in this particular direction, when it reveals something so vast and so consistent, and so improbably orderly that you genuinely do not have a good response except to sit with it quietly and let it be what it is. This is one of those moments. The same rules, everywhere, always, and us, here, briefly inside them. Let's go somewhere we have not been yet. We have talked about what quantum mechanics says about particles and waves and measurement and entanglement. But there is something we have not talked about, which is what quantum mechanics says about how particles interact with each other. Forces. In classical physics, forces are things that one object exerts on another, transmitted through a field. Gravity, electromagnetism. Objects push and pull each other through these fields, and the field mediates the interaction. In quantum mechanics, forces are described differently. They are mediated by particles. The electromagnetic force between two electrons, the repulsion that keeps them apart, that keeps atoms from collapsing into each other, that keeps your hand from passing through a table, is, in quantum field theory, transmitted by photons, virtual photons. The two electrons exchange photons, and it is this exchange that produces the force between them, not contact, not action at a distance in the simple sense. Exchange of particles. The strong nuclear force, which holds quarks together inside protons and neutrons, and which holds protons and neutrons together inside the nucleus, is mediated by particles called gluons. The weak nuclear force, responsible for certain types of radioactive decay, is mediated by particles called the W and Z bosons. Gravity, in general relativity, is described as the curvature of space-time produced by mass and energy. In a quantum theory of gravity, it is expected that gravity would also be mediated by a particle called the graviton. But quantum gravity, as we mentioned, remains an unsolved problem. The graviton has not been observed. Except for that gap, the picture is remarkably clean. The matter particles, electrons, quarks, and a few others, interact by exchanging force-carrying particles. The interactions are precise and quantized. The force-carrying particles are themselves quantum objects, subject to superposition and uncertainty and all the rest. The entirety of matter and energy, and their interactions described, in this framework as a dance of quantum fields. Every force, every interaction, every push and pull and repulsion and attraction in the universe, at the bottom, quantum, the table that holds your glass of water, electrons in your hand, repelling electrons in the table's surface, exchanged virtual photons between them, giving the sensation of solid resistance. The oxygen you breathe binding to the iron in hemoglobin, the light reaching your eyes in the morning, all of it, quantum field interactions, all of it, ripples in fields exchanging particles, all of it, completely, astonishingly normal, from inside it, the strangeness invisible from the inside, because you are entirely made of it and have never experienced anything else. You have never felt a force that was not quantum mechanical at its root. You have never touched anything that was not quantum mechanical. You have never seen anything that was not quantum mechanical. You are the inside of the quantum world, experiencing the quantum world, and it feels like ordinary life, which is remarkable, not unsettling, remarkable. Let's come back down from that altitude for a moment. Let's be very specific and very small. An atom of oxygen, right now, inside your lungs, attached to a hemoglobin molecule in a red blood cell, moving through the blood, through an artery, carrying that oxygen somewhere in your body. That oxygen atom has 8 protons in its nucleus, and 8 neutrons, and 8 electrons arranged in 2 shells around the nucleus. The innermost 2 electrons are in the lowest energy orbital, the 1s orbital, a spherical cloud of probability centered on the nucleus. The next 6 electrons are in the second shell, distributed among the 2s orbital and the 3 2p orbitals. Each of these electrons exists, right now, as a probability distribution, a cloud of where it might be, a smear of quantum uncertainty, obeying the Pauli exclusion principle, occupying its quantum state with the perfect indifference of something that has been doing this since long before any of this had a name. The nucleus, 8 protons and 8 neutrons packed together, is held in that compact arrangement by the exchange of gluons between the quarks inside each nucleon. The whole atom is held together by the exchange of virtual photons between the electrons and the nucleus. The red blood cell is moving because of pressure differences in the blood, which come from the contraction of the heart, which is controlled by electrical signals, which are carried by the movement of ions across cell membranes, which is itself a quantum chemical process. And all of this is happening right now, inside you, without any awareness or effort on your part, without any direction, without any consciousness guiding it. Quantum mechanics, running itself, producing life, your life, without waiting to be understood, without needing permission, just proceeding, the way it always has. There is something in this that goes past comfort into something quieter. Not comfort exactly, more like the feeling of being somewhere very large and very old and very steady, somewhere that has been here a long time and will be here after everything you know has changed. The quantum rules are not going anywhere, not changing, not subject to any of the ordinary sources of uncertainty in a life. They are deeper than all of that, more permanent. The rules underlying the rules underlying the rules, all the way down, and then the rules themselves at the bottom. You are resting on top of something very solid, even though it is also very strange, even though the most solid thing in it is a cloud of probability. That is allowed. The probability cloud is what solid actually is, all the way down. Let's go somewhere a little sideways. Physics is full of conservation laws. The idea that certain quantities are preserved through any interaction, no matter what else changes. The total energy of an isolated system does not change. The total momentum does not change. The total electric charge does not change. These are not imposed from outside. They follow through a beautiful piece of mathematics called Noether's theorem, from the symmetries of the laws of physics. Energy conservation follows from the fact that the laws of physics do not change over time. Momentum conservation follows from the fact that the laws of physics are the same in all locations. Charge conservation follows from a more abstract symmetry in the quantum mechanical description of the electromagnetic field, the permanence of the quantum rules, the sameness of the laws everywhere. These are not just convenient facts, they are the reason that anything is preserved at all. The conservation laws that keep the energy in your body, that keep the charge in every atom you are made of, that keep the momentum that carries you through your day, all of it is a consequence of the universe having consistent laws that do not change as you move through space and time, which closes a quiet loop. The consistency we marveled at earlier, the same fingerprint of hydrogen in stars a billion light-years away, is the same consistency that gives rise to conservation laws, which are what make the world stable enough to live in. If the laws changed from place to place, energy would not be conserved. If the laws changed over time, energy would not be conserved. The world would be unstable in ways that would make life impossible. The fact that the laws are the same everywhere and always is not just philosophically impressive. It is what makes physics work. It is what makes anything work. The universe, in choosing consistent rules, or rather, in simply having consistent rules, since there was no choosing involved, happened to make persistence possible, made memory possible, made identity possible, made you possible, and let you lie here, now, at the end of this, beginning to feel the edges of sleep, the thoughts getting just slightly softer, the connections just slightly more relaxed, the body settling into the rules it has always been following without knowing it. Let's stay a little longer. There are things still worth saying, and the night is patient, and there is no hurry. We talked about quantum tunneling and how it powers the sun, but there is a subtler place where tunneling matters, and it is one that connects to the origin of the universe itself. In the very early universe, as it cooled and expanded from an extraordinarily hot and dense initial state, there were periods where different kinds of phase transitions occurred. The universe changing from one state to another, the way water changes from gas to liquid to ice. In some models of early universe physics, including versions of cosmic inflation, the idea that the very early universe underwent an extremely rapid expansion, these transitions involve quantum tunneling, the universe tunneling from one configuration, one false vacuum state, to another. A false vacuum is a state of the universe's quantum fields that appears stable locally, like a ball resting in a shallow valley on a hillside, but which is not the lowest possible energy state. Given enough time, or through quantum tunneling, the system can transition to the lower energy state, the true vacuum, even without the classical energy required to jump over the barrier between them. Some physicists have raised the question of whether the vacuum state our universe currently occupies is the true vacuum or a false one. I want to be very clear about this. This is a theoretical possibility, not an established fact. The question of whether the electroweak vacuum of our universe is stable or metastable, whether it is the lowest energy state or a local minimum that could someday tunnel to a lower state, is an active research question in particle physics. The answer depends on the precise values of the top quark mass and the Higgs boson mass, which have been measured, but with uncertainties that matter for this calculation. Current evidence suggests the vacuum is either stable or metastable on a timescale enormously longer than the current age of the universe, which means that if there is any risk associated with this question, it is not relevant to any human timescale. But the existence of the question is interesting in itself, because it is a reminder that even the vacuum, the stage on which everything happens, is a quantum system, subject to quantum rules, potentially subject to quantum fluctuations, the background of the universe as a quantum object, and the universe we live in, with its specific particle masses and force strengths and vacuum energy, as one particular quantum configuration out of whatever configurations are possible, one particular answer out of a space of possible answers, the one that we are inside, for now, for an extraordinarily long time, longer than any meaningful comparison can easily capture, long enough to call it effectively forever from the perspective of a life. Let's close this section of the journey with something that is, I think, genuinely worth sitting with. All of quantum mechanics, all the superposition and uncertainty, and entanglement and tunneling, and wave-particle duality, all of it can be traced back to a single, simple, deeply strange fact. The world is made of things that behave like waves. That is it, not a list of exotic phenomena, one underlying fact from which everything else follows. Waves interfere. Waves spread out. Waves can be in many places at once. Waves have frequencies and wavelengths that are linked by uncertainty relations. Waves can be entangled across space. Waves tunnel through barriers. All of quantum mechanics is the physics of waves, applied to matter. The strangeness of quantum mechanics is the strangeness of waves, taken seriously at every scale. And waves are not unfamiliar things. You have seen waves your entire life. On water, in sound, in light, waves are everywhere. The only truly strange thing quantum mechanics adds is the idea that matter, actual, solid-seeming matter, is also wave-like. That the electron is a wave, that the proton is a wave, that you are, at the fundamental level, a very complicated interference pattern of quantum waves. Which is strange, yes, but also, somehow, recognizable. The universe speaking in a language that everything is, simultaneously, native to, including you, the waves in you, made of the same stuff as the waves in everything else, following the same rules, right now, without interruption. Let's keep moving. There is a topic we have circled without entering, and it is time to go inside it. The question of why the quantum world is the way it is, rather than some other way. Not the history of how we discovered it, not the mathematics of how we describe it. The deeper question, why these rules? Why should matter be wave-like? Why should measurement collapse a superposition rather than something else? Why should entanglement be non-local in the way it is? This is a question that physics, strictly speaking, does not answer. Physics describes how the universe behaves. It builds models that predict observations. It reveals structure and symmetry. But the question of why the universe has the particular structure it has, why the laws are these laws rather than other laws, is a question that sits at the edge of physics and spills over into philosophy. And I want to be honest about that. Some physicists think the question is answerable in principle, that a deep enough theory would explain why the laws must be what they are, that the universe could not have been otherwise. Others think the question is not a physics question at all, that the laws are a brute fact, and the best we can do is describe them. Others are drawn to the idea of a multiverse, where many different sets of laws are all equally real, and we find ourselves in this particular set because it supports our existence, which makes the question of why these laws a question about observer selection rather than about the laws themselves. None of these positions is currently provable. All of them are seriously held, and the honest answer, for now, is we do not know. The laws are these laws, and they produce this world, and inside this world, for a brief and improbable stretch of time, there are things that can wonder about the laws. We are those things. Wondering, right now, in the dark. The wondering is itself a quantum process, in the sense that it is a process running in a brain made of atoms following quantum rules. The neurons firing, the ions moving, the proteins folding, all of it quantum mechanical at the base. The laws producing the ability to question the laws, which is, whatever else you want to say about it, extremely interesting. Let's go just a little deeper into the question of many worlds, because it is genuinely interesting, and because the way it is usually presented in popular contexts tends to either overclaim or underclaim what it actually says. The many worlds interpretation of quantum mechanics, sometimes called the Everett interpretation after Hugh Everett, says that the wave function is the complete description of reality, that it never collapses, that it simply evolves according to the Schrödinger equation at all times without exception. When a measurement occurs, in this picture, the wave function does not collapse into one outcome. Instead, the measuring device and the observer and everything else in the room all become entangled with the quantum system being measured. The total wave function of everything includes components corresponding to each possible outcome. Each component continues to evolve independently, no longer able to interfere with the others due to decoherence, each one containing a version of the observer who experiences one particular outcome. No branch is privileged, no branch is selected, all branches continue. What this means is that when you toss a fair quantum coin, when you make any quantum measurement with multiple possible outcomes, there is a sense in which all outcomes occur. Every outcome occurs in some branch of the wave function. Every branch contains a version of you experiencing that outcome. What you experience is one branch. Other branches contain other versions of you, equally real, experiencing other outcomes. There is no fact of the matter about which version of you is the real one from the theory's perspective. They are all equally real. This is, to put it gently, a very large claim. It requires the existence of an enormous, possibly infinite, number of equally real parallel worlds, branching at every quantum event, forever. It requires taking the mathematics of the wave function with absolute, total seriousness. No collapse, no selection, just branching. The reason this interpretation is taken seriously, and it is taken seriously, is that it achieves something important. It eliminates the need for the mysterious collapse postulate. In Copenhagen, you have to stipulate, as an extra rule, that wave functions collapse upon measurement. In Everett, you do not. The Schrödinger equation does everything. No extra rule. The cost of eliminating that mysterious rule is an infinite proliferation of worlds. Many physicists consider that a reasonable trade. Many do not. The debate continues. What the many worlds interpretation does not mean is a universe full of identical copies of you living different lives, making different choices, in ways that are somehow accessible to you. The branches are causally isolated. After decoherence has occurred, the branches cannot interfere with each other. You cannot communicate with another branch. You cannot feel its existence. The other you in another branch is not you in any operationally meaningful sense. So the popular science fiction version of parallel worlds, where you can jump to the branch where you made a different choice, is not what Everett is saying. Everett is saying something more subtle and more strange, that the universe contains many copies of your history, all equally real, none of which you have any access to, which is a strange thing to believe and which may be true, or may not be. The experiments for now do not decide. But the question itself is beautiful, and sitting with it, without needing to resolve it, is one of the pleasures available to someone lying quietly in the dark, letting their mind range where it will, uncommitted to a conclusion. The outcome of tonight's wondering is not required. The universe has not asked you to decide. It is in its own way, still deciding too, or branching, or collapsing, depending on which interpretation you prefer, all of which leave you right here in exactly this moment as you are, breathing, thinking, more slowly now, the thoughts spacing themselves out a little, the edges of ideas getting softer. Let's stay in this register for a while. We have covered an enormous amount tonight, and rather than keep adding new pieces, it feels right to move more slowly now, to take the ideas we have already opened and let them breathe a little more. Consider entanglement again, not the physics of it, the feeling of it. Two particles, far apart, described by a single wave function, correlated in a way that does not travel through space. The correlation is not a thing that moves from one particle to the other. It is more like a shared fact that they both participate in, simultaneously, without a mechanism, without a signal. And what that implies, if you follow it far enough, is that the universe cannot be fully described as a collection of separate, independent parts. Entanglement is evidence that reality has a kind of non-local wholeness, that the whole is not simply the sum of its parts, because the parts can be correlated in ways that cannot be accounted for by any local story about each part individually. The universe is, in some sense, one thing, divided, yes, spread across an enormous span of space and time, containing parts that are for most purposes completely independent. But underneath that independence, at the quantum level, woven together in ways that cannot be fully untangled, that is not a spiritual claim. It is a claim that follows from Bell's theorem and the experiments. The universe cannot be fully described by a theory of independent local parts. Something about it is irreducibly whole, which may be the thing that makes everything else work. The consistency of the laws everywhere, the non-local correlations of entanglement, the vacuum fluctuations connecting the smallest scales to the structure of the cosmos, all of it pointing toward a reality that is, at the deepest level, unified in some way we do not yet fully understand. Not mystically, mathematically, structurally, the universe cohering, without being asked to, just because that is what it does. You are part of that coherence right now, not just in the philosophical sense. In the physical sense, the atoms in your body are entangled at the quantum level with the atoms they have interacted with over the course of their existence, with the air you have breathed, with the food you have eaten, with everything you have touched, with the light that has reached your eyes. Not entangled in ways you can detect or measure, not entangled in ways that give you non-local access to information about distant things, but entangled, technically, in the sense that quantum mechanics describes. The boundary between you and the rest of the universe is not as sharp as it feels. At the quantum level, you are slightly entangled with everything you have ever touched, in a web that extends back through time to the first moments of your existence. And before you existed, the atoms that became you were part of the universe for billions of years before that, interacting with other atoms, accumulating entanglements of their own. The web is very old, and you are a part of it, a particular, temporary, improbably organized part of it, but part of it. Let's go a little further. There is a way of talking about quantum mechanics that I have been careful to avoid tonight, and I want to explain why. The language of quantum physics proves that consciousness creates reality, or quantum mechanics shows that the observer affects the observed, so you shape your own reality, is very common in certain popular discussions, and it takes real things and puts them in a frame that is misleading in a way that matters. The observer effect is real. Measurement does affect quantum systems. Consciousness is, presumably, a quantum process in the sense that it runs in a brain made of atoms. All of that is true, but the jump from those true things to your thoughts shape reality, or consciousness creates the physical world, is not supported by the physics. It is not what the equations say, it is not what the experiments show. The observer in quantum mechanics, as we discussed, is a physical measuring device interacting with a quantum system. It is not a mind. The collapse of the wave function, whatever it is not something that requires human consciousness to proceed. An electron passing through a double slit behaves the same way whether anyone is consciously watching the results or not. The universe was running quantum processes for 9 billion years before the Earth existed, and for another 4.5 billion years before humans evolved, without anyone's consciousness present. Whatever the observer effect is, it does not require human observers. This matters because the mystical version of quantum mechanics is, in some ways, a way of making the strangeness of quantum mechanics smaller, of reducing it to something familiar and human scale, something about the power of our attention and our intention. The actual strangeness is much larger than that. It is not about us. It is about the structure of reality at every scale, in every place, at every time, regardless of whether anything with consciousness is anywhere nearby. The universe does not need us to be strange. It was strange before we arrived. It will be strange after we are gone. Our presence is not what makes it remarkable. Our presence is just one of the remarkable things in it, which is, if you let it be, more humbling and more beautiful than the version where our consciousness is running the show. We are inside something extraordinary, not because we created it, not because we are its purpose, but because that is where we happen to be, which is enough, more than enough. The quiet fact of being inside something vast and strange and consistent and ruled by mathematics that no one asked for and no one could have predicted. Just here, just this. Let's sit with the double slit one more time, not to learn something new from it, just to feel it again, more slowly. A single electron, emitted from a source, traveling toward a barrier with two slits. No one tells it what to do. The laws tell it what to do, and the laws say, spread out, be a wave, pass through both slits, interfere with yourself, arrive at the screen as a single dot, at a location determined by probability. The electron does this, every time, without deviation, without confusion, without apparent effort. It does what quantum mechanics says it should do, not because it knows the rules, not because it has been instructed, not because anyone is watching, but because quantum mechanics is not a description imposed on the electron from outside. Quantum mechanics is what the electron is, what electrons are, what everything is. The rules are not rules in the sense of laws that could be broken but happen not to be. They are what existence looks like from the inside, and you are inside them, right now. The electron doing its wave-like thing in the atoms of your hands. The uncertainty principle operating in every nucleus in your body. The Pauli exclusion principle arranging the electrons in every atom you are made of. The whole silent machinery running, never pausing, never consulting you, just proceeding, the way it has always proceeded, the way it will always proceed. Long after the particular arrangement of atoms that is you has dissolved back into the universe and become parts of other things, other stars maybe, other planets, other arrangements of atoms that we cannot yet picture, the atoms themselves going on, quantum mechanically, in whatever configuration they find themselves in next, carrying no memory of you, but carrying the quantum properties they have always had, the same spin, the same indistinguishability, the same uncertainty. There is something in that which is not sad, if you let it be not sad. The atoms are not lost, they are just elsewhere, still obeying the same rules, still spread out in their probability clouds, still entangled with whatever they have touched. The universe does not discard anything, it rearranges, always rearranges, from one configuration to another, following the laws, conserving what must be conserved, releasing what can be released, into new patterns. You are a configuration that became briefly aware of the laws that produced it. That is a remarkable thing to be. And then the configuration changes, and the laws remain. Let's come back to something more immediate, more present. The room you are in right now, not the physics of it, just it. The particular quality of dark behind your eyes, the weight of things, the sound, if there is one, of the building settling, or the street outside, or the particular silence of wherever you are. All of that is quantum mechanics. Not in the sense that it feels quantum mechanical. It does not. It feels like a room. But underneath the feeling of a room, at the level where the walls are made of atoms and the atoms are made of electrons and nuclei, and the electrons are doing their probabilistic thing, and the nuclei are held together by gluons, and the whole arrangement is producing the sensation of solidity by exchanging virtual photons between the electrons in your skin and the electrons in whatever you are touching, underneath all the familiar texture of a room, the same strange rules. The same wave-like electrons, the same uncertain positions, the same non-local entanglements woven through the history of every atom. The room is a quantum system, a very large, very decohered, very classical-seeming quantum system, but quantum all the way down, and you, in the room, are the same. Quantum all the way down. The thought of that, if you hold it in a certain way, feels less like a scientific fact and more like a kind of companionship. You are not separate from the rules that govern the stars. You are made of the same matter, following the same rules, participating in the same processes. The iron in your blood was made in a star that died before the sun existed. The hydrogen in your water has been hydrogen since the first few minutes after the Big Bang. You are, in a very literal sense, ancient. Your atoms are ancient, their quantum properties unchanged from the beginning of the universe. The universe, in some sense, has been carrying the atoms that became you since almost the very start, for 13-odd billion years, and for a few decades, it arranged them in a way that thinks and breathes, and lies in the dark, and wonders about quantum mechanics. And now, in this particular moment, it is arranging them in a way that is slowly becoming less wakeful, the thoughts spreading out, like a wave function, a little less localized than before, a little less committed to a specific position, drifting. Let's drift a little with the ideas before setting them down. We talked about the many worlds interpretation and the Copenhagen interpretation and a few others, but there is one more I want to mention, not because it is more likely to be correct, but because it is the most philosophically interesting and the most unsettling in a specific, precise way. It is called the relational interpretation, and it was proposed by Carlo Rovelli in 1996, a physicist known primarily for his work in loop quantum gravity. The relational interpretation says that quantum states are not absolute, not real independent of everything else. A particle does not have a quantum state in isolation, it has a quantum state relative to a particular observer, or more precisely, relative to a particular physical system that interacts with it. In other words, the wave function of a particle is not a description of the particle's absolute state. It is a description of the particle's state as it relates to some other system, and different systems, different observers, different measuring devices can consistently assign different quantum states to the same particle, without any of them being wrong. Reality, in this picture, is not a single set of facts about how things are. It is a web of facts about how things relate to each other. No system has properties that are observer-independent in the quantum sense. Everything is relative. Not in the sense that truth is subjective or that facts are matters of opinion, but in the precise physical sense that quantum states are relational. The particle has spin-up relative to one observer and spin-down relative to another, and neither observer is wrong, because there is no observer-independent spin to be right or wrong about. What ties this all together, what prevents the world from becoming a completely arbitrary fog of conflicting facts, is the consistency of the correlations. When two observers eventually compare their notes, they find that their observations are consistent with each other. The correlations are real. The individual facts are relative, but the relationships between facts are not. Which means what is fundamental in this picture is not things, not properties of things, but relationships. The universe as a web of relations, no foundation below the relations, relations all the way down, which is, as I said, the most philosophically interesting and the most unsettling of the interpretations, in a way that is hard to pin down, but which you might feel if you think about it long enough. What are you, if not a thing? If you are a collection of relations, the way your atoms relate to each other and to the rest of the world, and the way the signals in your brain relate to each other, producing the experience of being something rather than just a process, what does that say about what it feels like to be you? Ravelli would say, it says exactly what experience is. Experience is relations. What it feels like to be a conscious observer is what it feels like to be the kind of relational process that quantum mechanics describes. Feeling is what relations feel like from the inside, which is either very deep or a bit circular, and perhaps both. And perhaps being a little circular is not the worst thing, if the circle is large enough and interesting enough to be worth going around. Let's go around it slowly. The relational interpretation places special weight on what happens when two systems interact. When an electron passes through a slit and is detected, the detection is a correlation between the electron and the detector. That correlation is real. What existed before the detection, the electron's state in itself, independent of the detector, is not something the theory speaks to, according to Ravelli. It is not a meaningful question. Only the interaction is real. Only the correlation is real. The electron before detection does not have a definite position, because there is no system interacting with it in a way that would make position definite. Position becomes definite in the context of a position measurement. Spin becomes definite in the context of a spin measurement. Reality is, at the quantum level, an ongoing process of interactions creating momentary facts that are then immediately subsumed into the next interaction, a river of correlations. No bed, just the flowing. This is, I think, the most honest possible description of how it feels to follow quantum mechanics to its logical end and ask what it means. Not a world of solid objects with definite properties, not even a world of clouds and probabilities, a world of interactions, a world of relations, a world that is always in the process of being determined, never fully determined, always at the edge of the next interaction, the next correlation, the next tiny settling of one fact from the fog of possibility. And you, in this world, are one of the processes through which correlations accumulate, through which the fog, for a moment, clears into a particular experience. The atoms in your body, not just existing in a superposition somewhere, but interacting with each other constantly, producing correlations, producing the relational network that is you. The you that you experience is the inside of that network. The warmth you feel, the slight weight of sleep settling over the edges of thought, the sound of your own breathing just barely audible, These are correlations. You correlating with your own experience, in the most literal quantum sense. That should feel strange. It does feel strange, if you look at it directly, and then it settles into something else. Something like recognition. Of course it is this way. What else would it be? The universe is made of interactions, and experience is the inside of an interaction. What else would the inside of an interaction feel like, except like something? Let's move. We have been very deep for a long time. Let's come back up, not all the way, but a little, to something more concrete, to real experiments in real labs. There is a class of experiments that has been done in recent years that is worth mentioning, because it pushes the boundaries of what we understand about the quantum and the classical in a very direct way. They are called quantum optomechanics experiments. The idea is to take a mechanical object, something with actual, visible, classical-seeming structure, like a tiny vibrating mirror or a silicon beam, something you could see under a microscope, and cool it down and isolate it enough to observe quantum behavior. In ordinary conditions, a vibrating mirror is a classical object. Its vibrations are driven by thermal fluctuations, by the random jostling of atoms from heat, and it behaves classically. No superpositions, no interference. But cool it down to temperatures close to absolute zero, a few thousandths of a degree above the coldest possible temperature, isolate it from vibrations, shine very carefully controlled laser beams on it, and you can bring the mirror to a state where it is vibrating in what is called the quantum ground state, the state of minimum possible energy, the state where it has as little energy as quantum mechanics allows. And then, from that state, you can do quantum things to it. You can put it into a superposition of vibrating and not vibrating. You can entangle it with photons. You can observe, directly, the quantum behavior of a macroscopic mechanical object. Not macroscopic in the human scale. These mirrors are microns across, much smaller than a grain of sand, but visible under a microscope, with actual mechanical structure, a real physical object that reflects light in the ordinary sense, and it quantum mechanically interferes with itself. In experiments that have been done, right now, in labs all over the world. This is not science fiction. This is science, and it is pushing the boundary of what we know about where the quantum world ends and the classical world begins. With every experiment that succeeds, the line moves. A slightly larger object, shown to behave quantum mechanically, a slightly less isolated system, still showing quantum effects. The boundary retreating, and the retreat is not toward nothing, it is toward the understanding that there is no boundary, just decoherence, occurring faster and more completely the larger the system, but not absolute, not a wall, a gradient, and science, experiment by experiment, mapping the gradient, watching the quantum and the classical blur into each other, precisely and beautifully, exactly where the mathematics says they should. Let's think about photosynthesis, because it is one of the places where quantum mechanics may be doing something genuinely biological, in a way that was not known until recently, and that is still being actively studied. Photosynthesis is the process by which plants and some other organisms convert sunlight into chemical energy. Light hits certain molecules, excites electrons, and the energy of that excitation is transported to a reaction center where it can be used to do chemical work. The process has to be efficient, very efficient, and for a long time the efficiency was something of a puzzle, because in classical models of how the energy moves from the site of absorption to the reaction center, random hopping from molecule to molecule would waste too much energy. The path would be too random, too lossy. In 2007, Experiments using a technique called two-dimensional electronic spectroscopy revealed something unexpected. The energy transport in certain photosynthetic complexes shows signatures of quantum coherence. Long-lived oscillations in the way the energy is distributed among molecules, oscillations that last far longer than you would expect from classical thermal fluctuations. The energy is not hopping randomly, it is exploring many paths simultaneously. Like a quantum particle, it is finding the most efficient route through the molecular network by virtue of quantum interference. Some paths reinforced, some paths cancelled, the energy guided by quantum effects toward the reaction center much more efficiently than random hopping would allow. This is called quantum coherence in biology, and it was a surprising discovery, because biology is warm and wet and noisy, precisely the environment where you expect quantum coherence to dissolve almost immediately. The fact that it persists, in these molecular complexes, long enough to matter functionally, suggests that evolution may have discovered how to use quantum mechanics. May have. The research is ongoing, and the interpretation of the experiments is still being worked out. There are debates about what exactly the oscillations represent, and whether they are functionally relevant to efficiency. I want to be honest about that. But the possibility is being taken seriously. The possibility that life, over billions of years of evolution, found a way to exploit the quantum properties of matter, not by understanding quantum mechanics, not by having any concept of it, but by blindly finding, through selection, configurations of molecules that happen to preserve quantum coherence long enough to be useful. Evolution stumbling into quantum physics, which is either marvelous or expected, depending on how you look at it. If quantum mechanics is what matter is, then of course life, which is matter organized to be efficient, might find ways to use quantum properties. Of course it might. It would be strange if it did not, given enough time and enough selection pressure. And then there are the birds. Some migratory birds appear to navigate using the Earth's magnetic field, not just detecting the field, but extracting precise directional information from it. The mechanism proposed to explain this involves a quantum process in a protein called cryptochrome, found in the bird's eyes. A photon of light hits cryptochrome and creates an entangled pair of radicals, molecules with unpaired electrons, with quantum mechanical spins. The way the spins of this entangled pair evolve over time is sensitive to the direction and strength of the magnetic field. The bird's visual system, it is hypothesized, might be able to read the outcome of this quantum process as a visual signal, a kind of overlay on its visual field, providing directional information from the Earth's magnetic field. A quantum compass, built into the eye of a bird. Again, the research is ongoing, and the evidence is not yet conclusive. The quantum radical pair mechanism is a real and established quantum chemistry effect. Whether it is actually what the birds are using to navigate is the question still being answered. But the fact that nature has available to it a quantum mechanism precise enough to serve as a compass, and that birds do navigate by magnetic field, and that cryptochrome is present in their eyes, the hypothesis is not crazy. It is specific. It makes testable predictions. And some of those predictions have been tested and are consistent with the hypothesis. A bird flying south in autumn, its eye detecting the Earth's magnetic field through the quantum spin of entangled molecules. Quantum mechanics threading through the brain of a bird, threading through the migration of a species, threading through the ecology of the places those birds fly toward and away from. A quantum effect, cascading upward through biological scales to produce behavior you can watch from a window. The quantum world not separate from the living world, but threaded through it, quietly, without announcement. The way it is threaded through everything. Let's be quiet for a while, not silent, just quieter. The ideas have been coming quickly. and it is good to let them settle. To let what has already been said have space to mean something, rather than filling the space immediately with more. Somewhere in everything we have talked about tonight, there is a texture, a consistent feeling that runs through all of it, not just the strangeness. The strangeness is obvious. The deeper texture is something else. It is that the universe, for all its strangeness at the small scale, produces something at the large scale that feels coherent, consistent, navigable. The quantum rules, with all their uncertainty and superposition and non-locality, add up to a world where you can put a cup on a table and trust it to stay there, where you can throw a ball and predict very accurately where it will land, where you can make plans and build things and have expectations about the future, and more often than not, find those expectations roughly confirmed. The quantum weirdness does not bleed into everyday life. It stays where it is, below, behind, beneath, and the world above it is, for all practical purposes, the world Newton described, the world of ordinary causality, the world of objects with definite locations, the world of cause and effect, and predictable trajectories. The quantum and the classical, not in conflict, not competing, nested. The classical world emerging from the quantum world, the way a melody emerges from vibrating strings. The strings are vibrating in ways that are, at the level of individual atoms, entirely quantum mechanical. And out of all that quantum vibration comes something that you can hear as a single, coherent note. The quantum rules producing, at scale, the classical experience. By design, or not by design, by the mathematics, which is either a remarkable coincidence or evidence of something deep about the structure of nature. The fact that quantum mechanics, which is radically different from classical mechanics at the small scale, reproduces classical mechanics at the large scale, exactly, not approximately. The classical world is not a separate thing that coexists with the quantum world. It is the quantum world seen from a sufficient distance. This is called the correspondence principle. The quantum and the classical corresponding in the appropriate limit. The limit of large masses, large energies, many particles, where the math of quantum mechanics quietly becomes the math of classical mechanics. The handoff is seamless. You never notice the switch, because at the scales where you live, the switch happened so long ago and so completely that there is nothing to notice. The quantum is already gone by the time you arrive, already dissolved into the classical, and yet always there below it, always there. Let's talk about what happens very close to absolute zero, because there is something there that is strange in a different way from what we have been discussing, and it is worth a visit. We mentioned superconductors, the quantum state of electron pairs producing zero resistance. That happens in certain materials at very low temperatures. There is another phenomenon that happens in certain gases cooled to temperatures close to absolute zero. It is called a Bose-Einstein condensate, predicted by Satyendra Nath Bose and Albert Einstein in the 1920s. First actually created in a laboratory in 1995 by Eric Cornell and Carl Wieman, who shared a Nobel Prize for it. A Bose-Einstein condensate happens when you cool certain atoms. Atoms whose total spin is an integer, which makes them bosons rather than fermions, to temperatures so low that their de Broglie wavelengths become comparable to the distance between them, which means the quantum waves of neighboring atoms start to overlap, and overlap, and when enough of them overlap, something happens. All the atoms fall into exactly the same quantum state, not just similar states, the same state. They become a single quantum object, a macroscopic quantum object. Thousands or millions of atoms, all occupying a single quantum state, described by a single wave function, behaving as one. At this point, The condensate behaves in ways that have no classical analog. It flows without friction. It climbs up the walls of its container. If you stir it, the vortices it produces are quantized. They come in discrete units, not a continuous range. It is a quantum object at the scale you could in principle hold in your hand, or rather, at the scale of a tiny cloud of ultra-cold atoms, which is as close as anyone has gotten, and it is real. It has been made, many times, in many labs, with many different atomic species. The quantum world made briefly visible at a large scale, by removing heat, by reducing the chaos that normally drives decoherence, cooling atoms until their quantum nature reasserts itself, until the quantum and the macroscopic meet. The Bose-Einstein condensate is the quantum world peeking through into the everyday world. Not all the way. You cannot hold it. You cannot see it with the naked eye. It exists in a carefully controlled vacuum chamber, at temperatures colder than anything that exists naturally in the universe. But it exists, and its existence proves something important. It proves that quantum behavior does not have a natural upper size limit. It proves that with enough control, enough isolation, enough cooling, quantum effects can be seen at larger and larger scales. The limit is practical, not fundamental, which means, in principle, there is no size at which the quantum rules stop, only sizes at which they become harder to see. It is all quantum, all the way up. You just cannot feel it, because you are too warm, too tangled with the environment, too classical, but only because of your temperature, not because of your nature. Cool you down enough, cool anything down enough, and the quantum nature reasserts itself. The wave nature comes back, the superpositions become observable, the strangeness returns. It was always there, just hidden under the warmth. There is something very specific about that image. The quantum nature of matter not lost, not gone, not erased, just hidden under the warmth and noise of ordinary existence, waiting, in a sense, beneath the thermal chaos of a warm universe, always there. Patient, the way certain truths are patient, the way the night is patient, the way the body, when it is ready, will simply let go of the day without being asked. Let's go a little further still, into something I have been saving, because it connects everything we have talked about in a way that I think is worth arriving at slowly. We talked about quantum fields, the idea that particles are excitations of fields that fill all of space. The electron field, the photon field, the various quark fields, the Higgs field, which gives certain particles their mass. These fields are not separate things that happen to coexist. They interact with each other. They are coupled together. The electron field couples to the photon field, which is why electrons and photons interact, why light can be absorbed and emitted by atoms. The quark fields couple to the gluon field, which is why quarks are bound into protons and neutrons. The entire zoo of particles and forces is a network of coupled quantum fields. And what holds this network together, what gives it the specific structure it has, is a set of symmetries, mathematical symmetries. The laws of physics remain the same if you rotate your coordinate system. They remain the same if you shift your position in space. They remain the same if you shift your position in time. They remain the same under certain more abstract mathematical transformations, called gauge symmetries, that are harder to visualize but deeply important. Each symmetry corresponds, through Noether's theorem, to a conserved quantity. Rotational symmetry gives angular momentum conservation. Translational symmetry gives momentum conservation. Time translation symmetry gives energy conservation. The gauge symmetries give charge conservation and the existence of the force-carrying fields themselves. The electromagnetic field exists because the equations of quantum mechanics are invariant under a certain kind of phase transformation. If you rotate the mathematical phase of the electron field in a way that can vary from point to point, you need to introduce a compensating field to keep the equations consistent. That compensating field is the electromagnetic field. The photon is, in a precise technical sense, the particle that exists because the laws of physics have a certain symmetry. The forces of nature are, at their root, consequences of symmetry. The universe, at its deepest level, is symmetric, and the symmetries produce the forces, which produce the interactions, which produce the atoms, which produce the chemistry, which produces the biology, which produces the mind, which wonders about symmetry. The chain from the abstract mathematical symmetries of quantum field theory to the fact that something is wondering about those symmetries is a very long chain, but it is an unbroken one. Every link connects. From the symmetry of the equations to the atoms in the neurons that are, right now, slowing down, the firing rates decreasing, the connections between waking thoughts becoming a little more tenuous, the whole system drifting toward its own kind of symmetry. The symmetry of sleep, where the mind is not one thing or another, not fully here, not fully gone, somewhere in between, not so different, that liminal state, from a quantum system between measurements, potential, not yet actualized, possibilities not yet collapsed, drifting, in a superposition of thoughts, not quite any one of them. Let's drift there together for a little while. The room is what it is. The dark is what it is. The weight of your body in the bed is exactly what it is. The result of 4.5 billion years of planetary history and 13 billion years of cosmic history and a vast chain of quantum events, adding up to exactly this configuration of atoms in this particular room, on this particular night. All of it adding up to this exact moment, this breath, this slowing. There are things we have not yet fully covered. We will cover them. There are still layers to go through, still ideas to unfold, still the return journey from the quantum world back to the familiar world, back to the body, back to the room, back to the specific, ordinary miracle of waking life. All of that is still ahead, but for now, let the ideas that have already arrived settle. Let the double slit be what it is. Let the entanglement be what it is. Let the uncertainty principle be what it is. Not problems to be solved, not paradoxes to be resolved, just features of a universe that is doing something extraordinarily interesting at every scale, including the scale of your body, including the scale of your breath, including the scale of the thought that is right now becoming a little softer at its edges, a little less insistent on being a thought, a little more like the space between thoughts, which is where the good rest lives, not in the thinking, in the space around it. Let's start again from somewhere slightly different, not from the experiments, not from the mathematics, not from the history of physics, from a question, a very simple question that most people never think to ask, because the answer seems obvious, and because the obvious answer turns out, under examination, to dissolve. What does it mean for something to exist? Not a philosophical question in the airy sense, a physical one. What does it mean for an electron to exist? It has mass, a specific, measured mass. It has electric charge, a specific, measured charge. It has spin. It interacts with other particles in specific, predictable ways. But where is it? That is the question that stops having an obvious answer. In classical physics, a particle exists somewhere. It has a location. Even if you do not know that location, it has one. The ignorance is yours. The location belongs to the particle. In quantum mechanics, the location, before measurement, does not belong to the particle. It is not hidden. It is not waiting to be revealed. It genuinely does not exist as a definite quantity. The electron exists, in the sense that it has mass and charge and spin, but it does not exist somewhere, in the sense of having a definite location, until it is found somewhere. Found, in the sense of physically interacting with something that establishes a location. This is what physicists mean when they say, quantum mechanics is not just about our ignorance. It is not that the electron is somewhere and we do not know where. It is that the electron is not somewhere, in the classical sense, until an interaction makes it somewhere, and then it is somewhere. And then it keeps moving, and then it is not somewhere again. The existence of a quantum particle is a series of interactions punctuated by intervals of non-location, intervals of genuine, physical indefiniteness, intervals of being, in the most literal sense available, nowhere, or everywhere, or more precisely, distributed across a probability landscape, present to varying degrees in various regions, not committed to any of them. This is what the wave function describes, not where the particle is, where it might turn out to be, and with what probability, if something interacts with it. And the wave function is not a limitation of our description. It is the description, the most complete description available, the most complete description possible, according to the theorems that have been proven and the experiments that have been done. There is no deeper level, no hidden layer, where the particle has a definite location that the wave function is failing to reveal. The wave function is it. The cloud of probability is not hiding the particle. The cloud of probability is the particle, which means particles, in the interval between interactions, are something more like potentialities than actualities, more like the possibility of a thing than the thing itself. And the physical world is built from these potentialities, tables and chairs and planets and stars, all built from things that are, at the base, potentialities, actualized by constant interaction, constantly becoming actual through the web of interactions that connects everything to everything else. The table is definite because its atoms are in constant interaction with each other and with everything around them. The definiteness is maintained by the density of interactions. The definiteness is a consequence of constant measurement, in the quantum sense. The world measuring itself continuously through the interactions of its own parts, and producing, through that constant self-measurement, the appearance of a world of definite things, of solid tables and reliable floors, and predictable trajectories. The classical world, as the result of the quantum world, constantly checking in with itself, constantly collapsing its own potential into the actual. The universe, in that sense, is not a finished thing that exists. It is a process of becoming, always at the edge of the next interaction, always in the act of making itself actual, never finished, never done, always in the present tense. Let's think about that for a moment. The universe in the present tense, always, not having already been decided, not playing out a script, becoming, at each interaction, what the next moment will be. Quantum mechanics is, in this reading, a theory of becoming rather than a theory of being, which aligns, interestingly, with some very old philosophical intuitions about the nature of time and change. Heraclitus, the ancient Greek philosopher, is famous for the idea that you cannot step in the same river twice. The river is always different, always new water, always in motion. The river as a process rather than a thing. Quantum mechanics says something similar about matter. The electron is not a thing, it is a process, a series of interactions that we name with a single word as though it were a stable object. The stability is real. The consistency is real. The electron's mass and charge and spin are the same in every interaction, but the electron itself, between interactions, is not a located thing. It is a pattern, a law, a set of rules about how interactions will proceed, expressed in space and time as a wave function, as a cloud, as a potential, as something without a definite location, moving through space in a way that has no classical analog until the next interaction pins it down briefly and then spreads it out again, and so on, forever, or for as long as the electron has not been absorbed into something else, which may be forever. Electrons, as far as we know, do not decay. The same electron can exist for the entire lifetime of the universe, being, spreading, interacting, being pinned down, spreading again, a process without end, which is, in its own way, a kind of permanence. Not the permanence of a fixed thing, the permanence of a pattern, the permanence of a law, the permanence of a process that has been running since the first moments of the universe and shows no sign of stopping. There is something steadying about that kind of permanence, not the solidity of a rock, the steadiness of a river, always moving, always the same river. Let's go somewhere that connects the very small to the very large in a way we have not fully explored yet. The early universe. Not the Big Bang itself, which is a moment too extreme for any current theory to describe with confidence, but the first fraction of a second afterward, and then the first seconds, and then the first minutes. In the first tiny fraction of the first second after the Big Bang, the universe was so hot and so dense that the conditions were nothing like anything that exists anywhere in the observable universe today. All four fundamental forces, it is believed, may have been unified into a single force, not four separate things. One thing. As the universe expanded and cooled, these forces separated out, one by one. Gravity first, then the strong nuclear force, then the electroweak force, separating into the electromagnetic and the weak nuclear force. Each separation a kind of phase transition, a change of state, like water freezing, like steam condensing, the universe cooling through a series of transitions, each one changing the structure of the forces and the particles that interact through them. By the time the universe was a few microseconds old, it had cooled enough for quarks to bind into protons and neutrons. Before that, the universe was so hot that quarks could not be bound. They existed freely, in a state called a quark-gluon plasma, a state of matter that has been briefly recreated in particle accelerators at CERN and at Brookhaven National Laboratory. For a moment, in a controlled environment, the conditions of the universe at a few microseconds old, recreated, in a machine, by people, the universe at its most extreme conditions, briefly glimpsed, studied. There is something remarkable about that. The universe in its infancy, in a state so extreme that we cannot sustain it for more than a tiny fraction of a second in the most powerful machines we have ever built. And we can make it, briefly, in a circle of magnets 27 kilometers around, the universe revisiting itself, in miniature, in an instant, through the effort of thousands of people over decades, which is both humbling and, in a quiet way, rather wonderful. The universe curious about itself, using the minds it produced to recreate its own early states, to examine itself from the inside. After the quark-gluon plasma, the universe continued to cool. The protons and neutrons formed. Then, over the next few minutes, in a process called Big Bang nucleosynthesis, those protons and neutrons combined to form the first atomic nuclei, mostly hydrogen, some helium, a small amount of lithium, The heavy elements, carbon, oxygen, iron, all the rest, came later, much later, forged in stars. But hydrogen and helium, the lightest elements, were made in the first few minutes of the universe's existence, through nuclear fusion, through quantum tunneling, as we mentioned, through the same quantum processes that power the sun today, the universe fusing its own first elements, in the first minutes. And those hydrogen atoms, or rather, those hydrogen nuclei, bear protons, waiting hundreds of thousands of years for the universe to cool enough for electrons to combine with them and form neutral atoms. That moment, about 380,000 years after the Big Bang, is called recombination, and it is special for a reason. Before recombination, the universe was so hot that atoms could not exist. Any atom that formed was immediately torn apart by energetic photons. Electrons were free, protons were free, and free electrons scatter photons very efficiently. The universe was opaque. Light could not travel far before being scattered. After recombination, the electrons combined with nuclei to form atoms. Neutral atoms scatter photons far less efficiently. The universe became transparent. Light could travel freely, and the light that was released at that moment, the light that flooded out as the universe became transparent, is still traveling today. It has been traveling for about 13.8 billion years, and it reaches us from all directions at a temperature that has been cooled by the expansion of the universe to about 2.7 degrees above absolute zero. It is called the cosmic microwave background, and it can be detected right now. There is a faint microwave signal reaching your body from all directions as you lie there. Not enough to feel, not enough to warm you, but there, the afterglow of the first light of the transparent universe, the oldest light we can see, a snapshot of the universe at 380,000 years old, reaching you tonight. Along with everything else that is reaching you tonight, the quantum fluctuations in the cosmic microwave background, those tiny variations in temperature from place to place, are the quantum fingerprints of the early universe. The primordial density fluctuations, stretched by inflation, imprinted in the first light, and those fluctuations over billions of years were amplified by gravity, became clouds of gas, became the first stars, became galaxies, became the structure of the universe, and the stars made elements, and the elements made planets, and on at least one planet, the elements arrange themselves into something that breathes and wonders. And that something is picking up the signal of the oldest light in the universe right now, passively, without trying. The body as a receiver of ancient light. The body as a place where the history of the universe arrives, and is, in a very small and unmeasurable way, absorbed. The cosmic microwave background photons passing through you, mostly, some absorbed, most passing through as though you were not there, because at the quantum level, you mostly are not there, mostly empty space, mostly fields, mostly potential, with very small amounts of actual matter relative to the volume you occupy. The ancient light passing through the spaces between your atoms, the spaces that are, at the quantum scale, not empty at all, but full of fields and virtual particles and quantum fluctuations, full of the same strangeness we have been sitting with all night. Let's rest here for a little while, in the image of the room you are in, receiving the oldest light, receiving it without knowing, the atoms in the walls, the atoms in the blanket, the atoms in you, all of them briefly and continuously touched by the ancient signal, all of them part of the same universe that produced that signal, all of them, in a sense, older than the stars. The hydrogen in you is as old as the universe. The hydrogen in the water in your body was hydrogen before the Earth existed, before the Sun existed, before the Milky Way existed in its current form. The hydrogen has been hydrogen for 13.8 billion years, changing configurations, part of gas clouds, part of early stars, part of supernovae, part of the material that condensed into the solar system, part of the oceans, part of the rain, part of the food chain, part of you, for a while, and then, eventually, part of something else, the universe recycling its hydrogen, using it for a while as part of a star, then as part of space, then as part of a planet, then as part of a living thing, then as part of something else again, the hydrogen patient, the hydrogen indifferent, the hydrogen obeying the same quantum rules it has always obeyed, in every configuration it has ever been part of. You are, among other things, very old hydrogen, organized, for a while, into something that breathes. Let's talk about something that connects the quantum to the question of time in a more personal way, the experience of the present moment. In physics, time is treated as a dimension. The fourth dimension, alongside the three spatial dimensions, events happen at locations in space-time. The past is not gone in any absolute sense. The events are still there, in the past region of space-time. The future is not yet in any absolute sense. The events are there, in the future region of space-time. This is the block universe picture, space-time as a four-dimensional block, past, present, and future, all equally real. Time as a dimension you are located in, not a flow you are caught up in. But this picture does not obviously match your experience. Your experience is of a moving present, of the past being gone, of the future being open, of now being different from then. Where does this experienced present come from in a universe described by quantum mechanics and general relativity? It is, genuinely, not entirely clear. The most common explanation involves entropy and the arrow of time. The second law of thermodynamics says that entropy, the measure of disorder in a system, tends to increase over time. The past has lower entropy than the future, and the experience of the present moving forward is, in this view, the experience of entropy increasing, the experience of order becoming disorder, of information about the exact state of things being lost into the environment, the arrow of time as an arrow of entropy. But why was the entropy low to begin with? Why was the universe, at the beginning, in a state of very low entropy, such that it has been increasing ever since? That is another question that does not yet have a fully satisfying answer. The universe began in a state of extraordinarily low entropy and has been heading toward higher entropy ever since. And the direction of that journey is what we call the direction of time, which is why time feels like it has a direction. Because entropy has a direction, and we are built from processes that increase entropy. Digestion, metabolism, thought, all entropy-increasing processes. The arrow of time is written into the chemistry of life, written into the quantum events that drive that chemistry, written into the fundamental statistics of how quantum systems evolve in the presence of many particles. You experience time passing because you are an entropy-increasing process, made of entropy-increasing processes, made of quantum events, that collectively produce an overwhelming statistical tendency in one direction. The direction you call forward, the direction toward which the night is moving, the direction in which sleep waits, a little further along the arrow, a little further toward rest. Let's go somewhere we have visited briefly and go a little deeper. The uncertainty principle. We talked about it in terms of position and momentum, and energy and time, but there is something more to say about what uncertainty actually is at the quantum level, and I think it is worth approaching from a different angle. The uncertainty principle is often described as a limit on what we can know. That framing is misleading. It is a limit on what exists to be known. When a particle has a well-defined momentum, it does not have a well-defined position. Not because we cannot measure the position, because the position is not well-defined. The particle does not have one. It is spread out. Its wave function is an extended, regular wave, smooth, periodic, covering a large region of space, which is exactly what a well-defined momentum looks like in the wave picture. A regular wave with a precise frequency has a precise momentum because momentum is related to wavelength and wavelength is related to frequency. But a regular wave with a precise frequency extends through space without any particular location. It is everywhere. Position, undefined. Momentum, very well defined. And the more you localize the particle, the more you confine its wave function to a small region, the more you need to add waves of many different frequencies to produce that localization. Like adding many different musical notes together to produce a brief, sharp sound. A single note lasts forever. A sharp click contains many frequencies, localized in time, but spread in frequency. This is Fourier's theorem. Expressed in terms of quantum particles, it is the uncertainty principle, not a philosophical limitation, a mathematical necessity. Waves cannot be both localized and single frequency. These are mutually exclusive properties, and particles are waves, and so particles cannot have both definite position and definite momentum. These are mutually exclusive properties, not because of our instruments, not because of our ignorance, because of what waves are, which means the uncertainty principle is not telling us something about the limits of knowledge. It is telling us something about the nature of existence, about what it is to be a quantum particle, about what it is to be a wave, about the deep mathematical structure that underlies every piece of matter in the universe. The universe, built from waves, is necessarily uncertain. Its waviness is its uncertainty. The two are the same thing, which means certainty, complete, perfect, unlimited certainty about the state of a physical system is not just hard to achieve, it is not possible, even in principle. It is not a feature of any possible universe built from waves. It is excluded by the mathematics. The universe is not a place where certainty lives. It is a place where probability lives, where potentiality lives, where the range of possible outcomes is always, at the quantum level, wider than one. And there is something in that, if you let yourself feel it, that is not unsettling. There is something in that which is, very specifically, like permission. Permission to not know, permission to not be certain, permission to exist in a state of not having all the answers. Because the universe, which is much older and much larger than any anxiety, is also in that state. The universe does not know where its electrons are. The universe does not have a certain answer to many of its own questions. The universe is comfortable with this. It has always been comfortable with this. It was born uncertain. It will remain uncertain. And from the uncertainty, through the probabilities, through the wave function collapsing into specific outcomes again and again and again, all of this emerged. The stars, the elements, the planets. You, born from uncertainty, living in uncertainty, at home in it. Even when it does not feel that way. Let's go back to something specific. Let's go back to an electron, a single electron, in an atom, in one of the molecules in the wall of the room you are in. The wall is made of material of some kind. Whatever it is made of atoms, and the atoms have electrons. And one of those electrons right now is in whatever quantum state it is in, occupying an orbital, a probability cloud, existing in that cloud with no definite location. The orbital has a shape. maybe a sphere, maybe a dumbbell, maybe something more complex. But whatever shape it is, that shape describes not a location but a probability, a landscape of where the electron might be found if something interacted with it. The electron is in the wall, and not in the wall, spread across the orbital, touching, in a probabilistic sense, a range of space, including the space of the room, including the air between you and the wall. Not enough to matter, the probability falls off very quickly outside the atom, but technically, the electron's wave function does not drop to exactly zero at the boundary of the atom. It drops very close to zero. Very, very close, but not zero, which means the probability of finding the electron outside the atom, though incredibly tiny, is not exactly nothing. The electron in the wall has a vanishingly small but non-zero probability of being found outside the wall, on your side, in the room, near you, not close enough to matter, not close enough to measure, not close enough to affect anything, but technically there, in that vanishingly tiny probability, the quantum nature of matter connecting everything to everything else, through tiny threads of probability, too small to feel, too real to dismiss. The atom in the wall reaching, with the smallest possible tendril of probability, into the space where you are. Everything slightly connected to everything, the room not as separate compartments, as a continuous quantum system, where the boundaries between objects are not walls but gradients, very steep gradients. Gradients that fall off so steeply they might as well be walls, but not walls, gradients, always gradients. There is a concept in quantum mechanics that I have been circling without naming directly, and I want to name it now. It is called quantum non-locality. We have touched it in our discussion of entanglement, but it is worth saying plainly. Quantum mechanics is a non-local theory. Not in the sense that information travels faster than light. It does not. Not in the sense that you can use entanglement to send a signal. You cannot. But in the sense that the complete description of an entangled quantum system cannot be given by specifying the properties of its parts independently. The correlations between entangled particles are not explained by any local story. Any story that says particle A had property X when it left the source, and particle B had property Y, and those properties are why the measurements are correlated. Bell's theorem proved that no such story can be correct. The experiments confirmed it. The correlations are non-local. They are a property of the whole system, not of the parts. The whole is not explained by the parts. The whole is fundamental. The parts are abstractions, useful abstractions, necessary abstractions, but not the fundamental thing. The fundamental thing is the wave function of the whole, which is not located in any part of the system. It is not in particle A. It is not in particle B. It is a property of both, together, described by a mathematical object that lives in a space with twice as many dimensions as ordinary space. Not in ordinary space at all, in what is called Hilbert space, an abstract mathematical space where the wave function of a system with n particles lives in a space with 3n dimensions. For one particle, 3 dimensions. For 2 entangled particles, 6 dimensions. For a system of 1,000,000 particles, 3,000,000 dimensions. For you, made of something like 7,000 trillion atoms, a space of unimaginably many dimensions. Your quantum state, the complete description of you, in quantum mechanical terms, lives not in ordinary 3-dimensional space, but in a space with a number of dimensions so large that the number has no name, and the quantum state of the universe, the wave function of everything, lives in a space larger still, a space whose dimension is the number of particles in the observable universe multiplied by 3, a number larger than anything that could meaningfully be written down, and the universe, in that enormous abstract space, is a single point, moving, evolving, according to the Schrödinger equation, a single wave function in an unimaginably large Hilbert space. That is a description of reality, not as a collection of things arranged in three-dimensional space, as a single quantum state in an abstract space so large that three-dimensional space is almost an irrelevant detail. Almost, because the three-dimensional space of your experience emerges from that abstract space, is somehow produced by it, in a way that is still, at the foundations, being worked out. The relationship between the high-dimensional Hilbert space of quantum mechanics and the three-dimensional space of experience is one of the deep, open questions in the foundations of the field. How does the world of ordinary space and time emerge from the abstract quantum description? The answer may involve decoherence, may involve the specific structure of the Hamiltonian, the operator that governs how the wave function evolves, may involve something about observers and their classical seeming experiences, is not yet in its complete form known. Another open question, another edge of the map, beyond which, territory still being explored. Let's come back from those heights. Let's come back to the specific and the immediate. There is a sound somewhere. The building, the street, the particular ambient sound of wherever you are. Whatever that sound is, it is produced by vibrations, air pressure waves, which are, at the molecular level, the collective result of air molecules being pushed and pulled by the vibrating source. Each air molecule obeying quantum mechanics, each collision between molecules a quantum event. The sound, at the base, a quantum mechanical phenomenon, and in your ear, the vibration of the air causes the eardrum to move. The movement of the eardrum is transmitted through the tiny bones of the middle ear, the stirrup, the smallest bone in the human body, transmitting the vibration into the fluid of the cochlea. In the cochlea, hair cells respond to different frequencies of vibration, each hair cell bent by the fluid. Ion channels in the hair cell membrane opening in response to the bending, ions flowing through, an electrical signal generated, a nerve impulse traveling up the auditory nerve to the brain, the sound processed, heard, experienced. Every step in that chain involves quantum mechanics. The ion channels opening are protein molecules whose conformation changes are driven by quantum chemistry. The nerve impulse is carried by ion gradients across cell membranes, maintained by protein pumps that work through quantum mechanical chemistry. The synapses between neurons release neurotransmitter molecules whose binding to receptors is a quantum chemical event. The experience of hearing is built, from the ground up, from quantum events. The sound reaching you is the world reporting to you through quantum mechanics. Everything you have ever heard, every voice, every piece of music, every rainstorm, every conversation, every last sound that has ever reached your ears and been heard, all of it, at the base, quantum, all of it carried to you through the same strange, probabilistic, wave-like, uncertain machinery, which has been working reliably every moment of your life, without fail, without effort, without your awareness, and which is, right now, perhaps detecting the sound of your own breathing, or the silence around it, the quantum machinery of hearing, alert and ready, waiting for the next vibration, peaceful, untroubled. Let's go to something that comes up, often, in discussions of quantum mechanics, and which deserves a more careful treatment than it usually gets. The question of determinism. Are the events of the future already determined by the state of the present? In classical physics, The answer was yes, in principle. Given a complete specification of the state of every particle in the universe at one moment, you could, in principle, calculate the entire future trajectory of every particle. The future was determined. The apparent randomness of everyday life was just ignorance. Hidden causes producing apparently random effects. Laplace, the French mathematician, described a thought experiment. An intelligence who knew the position and velocity of every atom in the universe at one instant could calculate the past and future of every event. A perfectly deterministic machine. Quantum mechanics breaks this. In quantum mechanics, even complete knowledge of the quantum state, the wave function, is not sufficient to predict specific outcomes. The wave function tells you probabilities. The outcome, when a measurement is made, is random within those probabilities, not random in the sense of hidden causes we cannot see. Random in the deepest sense the theory allows. The randomness is fundamental, irreducible, not explainable by any more detailed description. The Copenhagen interpretation says, measurement produces a random outcome drawn from the probability distribution given by the wave function, and that is the complete story. No further explanation, no hidden cause, fundamental randomness, which means the future is not determined, not because we cannot calculate it, because it is not there to be calculated. The future, in quantum mechanics, is not a fixed fact waiting to be reached. It is a range of possibilities, each with a probability, and which possibility actualizes is not decided in advance. It is decided, if decided is even the right word, at the moment of each quantum event, freshly, without prior determination. The many worlds interpretation handles this differently. In many worlds there is no randomness. The Schrödinger equation is deterministic. The wave function evolves according to a fixed law, with no randomness, no collapse. All outcomes occur in different branches. What looks like randomness is the subjective experience of finding oneself in one branch rather than another. Determinism at the level of the wave function, apparent randomness at the level of experience. Both interpretations are consistent with all known experiments. And so the question of whether the universe is fundamentally random or fundamentally deterministic remains, in a very precise sense, open, experimentally undecidable, at least with current tools, philosophically alive, being debated by serious people right now in various universities and research institutes and late-night conversations over coffee. And you, lying here, are not required to resolve it. You are not required to decide whether the universe is deterministic or not. The universe is proceeding either way, following the laws it follows, producing the future it produces, with or without your position on the matter. And either way, it is not a machine, not a clockwork, not something that could be fully predicted even in principle, either because of fundamental randomness or because the branching of many worlds makes the question of which future dependent on which branch you ask the question from. Either way, the future is open. Either way, what comes next is not written yet, which means, in some sense, anything can happen within the constraints of the laws, within the probabilities, within the structure, but within that structure, genuinely open, genuinely new, each moment. Let's slow the whole thing down even further. We are getting close to the end of a very long journey, and the journey home deserves to be as slow as the journey out. We went in, smaller and smaller, into the atom, into the electron, into the wave function, into the uncertainty principle, into entanglement, into the quantum fields, into the vacuum fluctuations, into the structure of space-time, into the open questions at the edge of everything we know, And now we turn around and begin the long, slow return. Not because the journey inward is finished. It is not finished. It will not be finished in your lifetime. But because the outward journey is also part of the whole thing. The return matters. Coming back from the quantum to the classical, from the uncertain to the familiar, from the strange to the comfortable, from the physics to the room, from the abstract to the immediate. Let's begin the return. Quantum events, happening at the smallest scale. In the atoms of the neurons of a brain, in the molecules of the cell membranes, in the proteins that regulate the flow of ions. Quantum events accumulating, their probabilities collapsing into specific outcomes, those outcomes combining, interacting, producing signals in neurons, signals combining, producing something that is, in the aggregate, a thought that arises from a quantum substrate, not caused by any specific quantum event, not reducible to any specific set of quantum events, but arising from the same substrate, the same uncertain, wave-like, probabilistic machinery. And the thought, whatever it is something like an awareness, something like an experience, something that knows it is there, that knows there are thoughts, that can notice itself noticing, that is aware of the room, of the dark, of the weight of the blanket, of the slowing of the breath. All of that experience arising from quantum events in a brain, all of that awareness built from the same stuff as the electron in the double slit, the same wave-like matter, the same uncertain substrate, producing somehow the specific, vivid experience of being here, being this, right now. The experience of right now is the most immediate thing there is, and it is built from the most abstract, most mathematical, most counterintuitive physics there is. The immediate and the abstract. The same thing, different scales. The quantum world and the experienced world. Not two worlds, one world. Seen from inside. You are seeing the quantum world from inside. The quantum world producing the eye that sees it. The wave-like electrons in the retina. The photons that arrive as excitations of the quantum electromagnetic field. The quantum chemical reactions that convert light into nerve signals. The quantum events in the neurons that process those signals. And somewhere in all of that, the experience of seeing, the experience of light, the experience of a room in the dark, which is the quantum world experiencing itself, through you, for now. You are how the quantum world looks from the inside. And from the inside it looks like a room, it looks like a bed, it looks like the particular weight of this night, this dark, this slow and settling quiet. It looks like everything ordinary and familiar and near, which is the most remarkable thing of all, that the quantum world from the inside looks like ordinary life, like a cup on a nightstand, like the sound of a building in the quiet hours, like the feeling of being almost asleep, almost not quite there, hovering at the edge of something that is not quite waking and not quite sleep. That liminal place, which is, if you think about it, not so different from what we have been describing all night. A state that is not quite one thing and not quite another, not fully here, not fully gone, somewhere between, the way a particle is somewhere between positions before measurement, the way a spin is somewhere between up and down before the magnetic field gets a reading, the way the universe, at the quantum level, is always somewhere between the last event and the next one, in the interval, in the gap. That is where you are right now, in the gap. And the gap, as it turns out, is where everything interesting lives. Not at the fixed points, not at the definite outcomes, in the uncertain middle, in the spread out wave function, in the probability cloud, in the place between. Let's keep returning, from the quantum to the room, from the abstract to the specific. Let's talk about what quantum mechanics has actually given the world in the most immediate, practical sense. Because there is still something here worth saying, and it connects the deepest physics to the most everyday surfaces of life in a way that closes a loop. The semiconductor. We mentioned it before. But let's make it more concrete. A semiconductor is a material. Silicon is the most common example, whose electrical conductivity can be precisely controlled. In a metal, electrons flow freely, high conductivity, always. In an insulator, electrons cannot flow, low conductivity, always. In a semiconductor, the conductivity is in between, and more importantly, it can be tuned, made higher or lower by adding impurities, by applying electric fields, by controlling temperature. The reason this tunability exists is quantum mechanical. In a crystalline material, the allowed energies for electrons are not continuous. They are organized into bands, ranges of allowed energy separated by gaps of forbidden energy. The band structure. The band structure is a purely quantum mechanical phenomenon. It arises from the wave nature of electrons interacting with the periodic arrangement of atoms in a crystal. The waves of the electron interfere with the periodic structure of the crystal. Some wavelengths interfere constructively, some destructively. The destructively interfering ones are forbidden. Gaps appear. In an insulator, the forbidden gap is large. Electrons cannot jump across it with ordinary thermal energy. No conduction. In a metal, there is no gap. Electrons can move freely. In a semiconductor, the gap is small enough that a carefully applied electric field or a small amount of added impurity can push electrons across it, making the material conductive. This is the transistor, a quantum mechanical sandwich, a region of semiconductor whose conductivity is controlled by an applied voltage, which can be used as a switch, on or off. 0 or 1, the binary logic of every computer, built from the quantum band structure of silicon, built from the wave nature of electrons, built from the interference of quantum waves with a crystal lattice. The processor in every computer, every phone, every digital camera, every car, every medical device, every airplane, every satellite, every power grid, every modern machine of any kind, all of it, built from quantum mechanics, not inspired by quantum mechanics, not loosely related to quantum mechanics, built directly from the quantum mechanical behavior of electrons in crystalline materials. You are surrounded by it. The device through which you are hearing this, whatever it is, the speakers, the chips, the memory, the wireless radio, the display, all of it quantum, all of it a practical application of the strangeness we have been sitting with all night. The strangeness is not just theoretical, it is in your pocket, it is in the walls of this room, in whatever electronics are here. It is in the lights, in the data, in the signal that carried this voice. Quantum mechanics, everywhere, already familiar, already ordinary, already so deeply embedded in daily life that no one who uses it thinks about it, the way no one thinks about atomic physics when they put a cup on a table. The quantum world already completely integrated into ordinary life, without ceremony, without announcement, just there, running, steady. Let's go somewhere else. Let's go back to the early universe one more time, but approach it from a different direction, from the question of why there is anything at all. We mentioned quantum vacuum fluctuations, the idea that empty space is not empty, that virtual particles emerge from and return to the vacuum constantly, that the vacuum has energy. In fact, the vacuum has a specific energy per unit volume, called the vacuum energy, or the cosmological constant, in the context of general relativity. And the value of this vacuum energy is one of the most puzzling numbers in all of physics. Quantum field theory, when you try to calculate what the vacuum energy should be, produces a number, a very large number, incomprehensibly large. The vacuum should, according to naive quantum field theory, have an energy density so enormous that it would cause the universe to expand or contract so violently that no structures could form, no atoms, no stars, no galaxies, no you. But the universe is not doing that. The cosmological constant, measured from observations of the universe's expansion, is a number, a very small number, incomprehensibly smaller than what naive quantum field theory predicts. The discrepancy between the theoretically predicted value and the observed value is about 120 orders of magnitude, 1 followed by 120 zeros. That is the largest discrepancy between a theoretical prediction and an observation in the history of science. By an enormous margin. Nobody knows why. This is called the cosmological constant problem, and it is considered, by many physicists, to be the most embarrassing unsolved problem in theoretical physics. Because something is making the vacuum energy almost exactly zero, compared to what it should be. Something is cancelling the enormous contributions from quantum field theory almost perfectly. Not perfectly. The observed vacuum energy is not zero. It is small, but non-zero. And the non-zero value is causing the universe to expand at an accelerating rate. The accelerating expansion, discovered in 1998, for which Saul Perlmutter, Brian Schmidt, and Adam Rees won the Nobel Prize. The universe expanding faster and faster, driven by the tiny residual vacuum energy, by the quantum energy of empty space. The strangeness of the quantum vacuum, operating at the smallest scale, driving the evolution of the universe at the largest scale. The two ends of the size spectrum, connected, through a number that no one fully understands, but which is, apparently, precisely what it needs to be for structures to form, for atoms to exist, for stars to burn long enough to make heavy elements, for planets to form, for life to arise, for minds to wonder about the cosmological constant. If the vacuum energy were much larger, the universe would have expanded too fast for anything to form. If it were much smaller or negative, the universe might have collapsed. The value it has, small, positive, mysterious, is one of the values that allows this particular universe to be the kind of universe it is, which raises the question of whether there is something to explain, whether the value is fine-tuned by some as yet unknown principle, whether it is one of many values in a multiverse, and we are here because this value works, whether the question of why is even the right question to ask. None of these options are settled, all are being explored. The cosmological constant is a number at the intersection of quantum mechanics and general relativity and cosmology and philosophy, a number that sits at the center of what we do not understand about the universe. And it is, in a way, a beautiful thing to not understand, because it is an invitation, the edge of the map, the place where the known world runs out, and beyond which something true is waiting, something we have not reached yet, something that, when it is finally understood, will probably seem obvious in retrospect, the way so many deep things do, but which right now is a genuine mystery, the universe keeping some of its secrets. Still, after all this, after all the experiments and the theorems and the Nobel Prizes and the particle accelerators and the satellites and the quantum computers, still some secrets, still some places the map does not go, which means the journey is not over, not for physics, not for science, not for the human project of trying to understand what this is. The journey is ongoing, and you are part of it. Not because you are a physicist, not because you have to be, but because you are made of the thing being explored. And the exploration happens inside you, at the quantum level, at every moment. You are the universe in the process of figuring itself out. Even asleep, even now, the exploration does not pause. Let's go somewhere very quiet, somewhere between the last idea and the next one. There is a concept in music called a rest, a moment of silence, not an absence of music, a structural part of the music, the silence that gives the notes their shape, the pause that makes the phrase mean something. In quantum mechanics, there is something analogous, the interval between interactions, the time when the wave function is simply evolving, spreading, unobserved, not collapsed into a definite state, just being what it is, a wave, moving, spreading, covering possibility. This interval is not nothing. It is not an absence. It is the quantum rest, the structural silence between events. And it is, in a sense, where most of the wave function's life is spent. The interactions, the measurements, the collapses are the notes. The intervals between are the rests, and the rests are where the quantum nature of the particle is most fully itself, unlocalized, unsettled, free to be uncertain, free to be spread across space, free to be in superposition, free to be what it is, the quantum rest. You are, right now, in something like a quantum rest, between the events of the day, between the demands and the decisions, between the measurements that the world makes of you, in the interval, spreading a little, becoming a little less certain of your own edges, a little more like the wave you are, underneath everything, the body settling, the mind settling, the quantum events in the neurons slowing, the firing rates decreasing, the coherent wakefulness that constitutes the day beginning to dissolve, not into nothing, into a different state. The way a wave function does not disappear between interactions, it changes, spreads, evolves into something less localized, less definite, more like possibility, less like a specific fact. And that spreading, that settling into possibility, is not a loss, it is a return to something prior to the specific, something larger than the particular thought, or the particular worry, or the particular fact that pressed itself so firmly into the foreground of the day, the particular dissolving back into the general, the specific outcome releasing back into the probability cloud from which it came, the return. Let's return more fully now. We have been all the way in. We have been to the wave function and the uncertainty principle and the quantum fields and the vacuum and the early universe and the cosmological constant and the open questions at the edge of everything. And now the return. From those depths, back up, through layers, quantum events producing chemistry, chemistry producing molecules, molecules producing cells, cells producing tissue, tissue producing organs, organs producing the body producing the experience of being in a room, in the dark, late, tired, breathing, each layer following from the one below, each layer producing something that the layer below does not obviously contain, chemistry producing life, life producing experience, experience producing the sense of being here, of being this particular person, in this particular room, on this particular night. The quantum rules, at the bottom of all of it, the strange, probabilistic, wave-like rules, producing, through uncountable layers of complexity, the specific texture of this moment, uniquely yours. One particular path through the space of all the possible outcomes of all the quantum events that have ever been relevant to you. Out of all the possibilities, this one, this room, this dark, this breath, this thought, becoming quieter, The quantum rules selecting, or not selecting, depending on your interpretation, this particular version of this moment, and you, inside it, the inside of a quantum event, extended over a lifetime, the long collapse of a very complicated wave function into the specific experience of being you, right now, which is, when you think about it this way, something to receive rather than something to accomplish. You did not produce this moment. You are this moment. The quantum rules produced you. The chemistry produced you. The biology produced you. The history of the universe produced you. And you are the experiencing of all of that, the inside of the producing, which does not require anything of you except being it, which you are already doing, which you cannot stop doing, even asleep, even in the deepest rest. The quantum events continue, the chemistry continues, the cells continue, the heart continues, the breath continues, you continue, without trying, without awareness. The way the universe continues, without trying, without awareness. Just proceeding, following the rules, producing the next moment from the last. Let's slow down even more. The ideas can rest now. They have come a long way. They have traveled from the surface of ordinary life all the way down to the quantum fields and back. They have earned their rest. Let them settle where they landed. Not organized, not resolved, not filed away, just settled, the way sediment settles to the bottom of a still pond. Not going anywhere, not needing to, just finding its level, the double slit, finding its level, the entanglement, finding its level, the uncertainty principle, finding its level, the vacuum fluctuations and the cosmic microwave background and the Bose-Einstein condensate and the Cooper pairs and the band structure of silicon and the quantum compass in the eye of a bird, all of it finding its level, not in a drawer, not solved, just settled, present in the mind the way a landscape is present when you have walked through it, not described, not catalogued, just known, in the body, in the way a particular quality of light stays with you even after the day it was part of is long over, the quantum world, settled into you, not as information, as experience. The experience of having thought about it, of having let it be strange, of having let the strangeness be gentle rather than threatening, of having spent time in a place where the rules are different, and returned to the ordinary world, not because the ordinary world is more true, but because it is where the body is, where the body always is, warm, located, in a specific room, on a specific night, breathing. Let's talk about what the return feels like. We went so far in, down past the molecule, past the atom, past the electron, past the nucleus, past the quarks, into the quantum fields, into the vacuum, into the abstract space of the wave function. And now, coming back, the quarks are still there, in their protons, in the nucleus. The electrons are still there, in their orbitals, in their probability clouds. The molecules are still there, in the cells, in the tissue. The tissue is still there, in the body. And the body is still here, in the room. Nothing has changed. The journey was not somewhere else. It was into what is already here. The strangeness was not imported from outside. It was always inside. Inside the ordinary. Inside the solid and familiar. Inside the room, and the blanket, and the body. All of that strangeness, always there, running quietly, without announcement, without requiring anything from you, just being what it is. The quantum nature of the room, the quantum nature of you, there together, have always been there together, will be there after this night is over, after sleep has come and gone, after the day begins, and the atoms resume their ordinary-seeming duties, the strangeness remains. Below everything, always below everything, the wave-like electrons, the uncertain positions, the entangled histories, the vacuum humming, the fields stretching in all directions. The ancient rules, unchanged. Let's come the rest of the way back, all the way to the surface, to the skin of things, to the place where the quantum becomes the classical and the classical becomes the world, the place where the probability clouds become solid-seeming objects, where the interference patterns become tables and floors, where the entanglement becomes the chemistry that makes cells work, where the uncertainty principle becomes the stability of matter, because matter is stable, partly because of quantum mechanics. The electrons do not spiral into the nucleus, not because of some classical balance of forces, because quantum mechanics forbids it. The uncertainty principle says, if you confine an electron to a very small region near the nucleus, its momentum becomes very uncertain, which means it must have a very large average kinetic energy. The more you confine it, the more kinetic energy it has. At some point, the kinetic energy cost of further confinement outweighs the potential energy gain from being closer to the nucleus. The electron settles into the orbital that minimizes the total energy, a stable state, the ground state, not falling inward, not drifting outward, settled, stable, because of the uncertainty principle, which means matter is stable because of quantum uncertainty. The solidity of the world is a consequence of the fundamental uncertainty of the world. The firm floor under the bed is firm because its electrons are uncertain. The wall is solid because its atoms are governed by a principle of irreducible indeterminacy. The stability and the strangeness are not opposites. The stability is produced by the strangeness. They are two faces of the same thing, the same rules, producing the uncertainty and the stability simultaneously, without contradiction, without conflict. The universe resolving what seems like a paradox simply by being what it is, not knowing it is resolving a paradox, just proceeding, the way it always does, the way it always will. Let's be very specific about where we are. The room, right now, the temperature of the air, a little cooler than your skin, the weight of whatever you are lying under, distributed across your body, the sound of your breathing, slow, regular, in, out, the dark behind your closed eyes, not black exactly, something more like deep red or grey, the faint light of the visual cortex doing its background work, the feeling of the surface beneath you, the slight adjustment your body makes without your noticing for comfort. All of that, all of it right now, all of it quantum mechanical at the base, and all of it right at the surface, perfectly ordinary, perfectly comfortable, the kind of ordinary that is so familiar it disappears, the kind of comfortable that you only notice in contrast, and underneath it, all the way down, the strangeness, the electrons in the atoms of your skin, in their probability clouds, the gluons holding the quarks together in the nuclei, the quantum fields pervading the space that is mostly what you are made of, the vacuum energy humming in the spaces between your atoms, the ancient cosmic microwave background photons passing through you, the entanglement between your atoms and the atoms they have interacted with over your entire life. All of it right there, below the comfort, below the ordinary, below the familiar, the quantum world and the experienced world, occupying the same space, being the same space. All night, they have been described as if they were two different things, the quantum and the classical, the strange and the familiar. But they are not two different things. They have never been two different things. There is only the one thing, the universe. seen from different distances, different levels of magnification, different scales. At the smallest scale, the wave function. At the largest scale, the cosmos. At the scale of a human body in a quiet room, the particular, temporary, extraordinary experience of being here, of being alive, of breathing, of thinking, more slowly now, of letting the thoughts come and go without holding them, of being a place where the universe pauses, briefly, to experience itself. Through you, tonight, the atoms that make you up have been in the universe since almost the beginning. They have been part of stars, part of gas clouds, part of oceans, part of other living things, part of the ground, part of the air, and for this particular stretch of time, they are part of you, organized into the specific, improbable pattern that is you, breathing, alive, aware, the awareness itself a quantum process, the most local thing there is, inside a skull, inside a room, inside a planet, inside a galaxy, inside a universe, which is, at the quantum level, one single wave function, one single, unimaginably complex quantum state, evolving, branching, spreading, settling, and you, inside it, a tiny and specific and entirely real part of that state, not a small part, not an insignificant part, the part that experiences, the part that wonders, the part that followed an idea all the way down into the quantum vacuum and all the way back up, and arrived here, back, in the room, in the dark, breathing, the quantum rules running quietly below everything, as they have always run, as they will always run, the electrons in their orbitals, the protons and neutrons in their nuclei, the quarks in their protons, the fields in the vacuum, all of it, proceeding, without needing your understanding, without needing your awareness, without needing your certainty. The universe does not need you to have resolved the measurement problem. It does not need you to have chosen between the Copenhagen interpretation and many worlds. It does not need you to know whether the wave function is real or just a calculational tool. It does not need you to have understood quantum entanglement in a satisfying way. It does not need any of that. It just proceeds, following its rules, producing its outcomes, spreading its wave functions, running its quantum events, and you can rest inside all of that, not because you understand it, not because you have resolved the strangeness, but because the strangeness is not a problem. It never was. It is just the way the universe is, the way it has always been, the way it was before anyone knew to call it strange, and the universe was fine, and the atoms were fine, and the electrons were fine, in their uncertain, spread out, wave-like, entangled way. They were fine. They are fine. They are fine right now, in you, doing exactly what they do, without distress, without effort, without any awareness that any of this is strange, because for them, it is not strange. It is simply what existing is, the way it has always been, the way it will always be. You can let the strangeness be fine too. You can let the uncertainty be fine. You can let the unresolved questions be fine. The universe has been comfortable with unresolved questions for 13.8 billion years. You can be comfortable for one night, this particular arrangement of the universe, this particular collection of atoms, this breath, this one, in, out, the electrons in your lungs accepting the oxygen molecules, the quantum chemistry running, the cells receiving what they need, the blood carrying it, the heart beating, steady, reliable, built from quantum events too small to feel, adding up to something unmistakably real, unmistakably here, unmistakably you, the strangeness at the bottom, the ordinary at the top, and somewhere in between, this long night of looking at both, of letting them be the same thing, of following the thread from the familiar all the way down to the fundamental and back, and finding, at the end of the return, that the room looks the same. The dark is the same dark. The breath is the same breath. But something is different, not in the room, in the way the room is held, a little more gently, a little more wonder in it, a little more awareness that the ordinary is not simply ordinary, that the familiar is not simply familiar, that underneath everything you have ever touched or seen or heard or breathed, the universe was doing something extraordinary, quietly, without announcement, just proceeding, as it always has, as it always will, the quantum world, your world, the same world, seen, tonight, from a different distance. And tomorrow, when the light comes back, and the day resumes, and the ordinary world reasserts itself with all its demands, and its solidities, and its predictable trajectories, the quantum rules will still be there, below everything, running, steady, the electrons in their clouds, the uncertainty in every position, the entanglement in every history, the vacuum humming, the ancient light passing through, all of it still there. You do not need to remember it. You do not need to think about it. You do not need to hold on to it. The universe will hold on to it. It has been holding on to it since before you existed. It will hold on to it after this night is over. You can let it go. The double slit. Let it go. The entanglement. Let it go. The uncertainty principle. The wave function. The vacuum fluctuations. The cosmological constant. The open questions. Let all of it go. It does not go anywhere. It is in the atoms of your hands and your face, and the cells of your eyes that are closed now, or nearly so. It stays, without your holding it, without your trying. The strangeness stays, the wonder stays, even asleep, even gone. The quantum events continue, the universe continues, you continue, in the only way that matters right now, breathing, present, in a room that is made of the same thing as the stars, in a body that has been part of the universe since before the earth existed, under a dark that is full of ancient light, following the same rules that make everything work, the simple rules, the strange rules, the only rules there are, and they are enough. They have always been enough. They made all of this from almost nothing, from a quantum fluctuation, from uncertainty, from the spread out, wave-like nature of everything. They made the stars and the heavy elements and the planets and the oceans and the cells and the minds. They made this room. They made this night. They made the thought that is now, finally, becoming too soft to hold, too gentle to follow, drifting, the way a wave function drifts between interactions, the way the day drifts into sleep, the way everything, eventually, returns to the quiet at the center of things, where the rules are still running, where the electrons are still uncertain, where the universe is still, quietly, extraordinarily, everything it has always been, and you are part of it, right now, in the gap between one moment and the next, in the interval, in the spread, in the not yet decided, in the gentle, particular ancient dark. Rest.